Light has no mass. It weighs nothing. You could hold 1 trillion photons in your palm and never feel the burden. And yet, right now, invisible beams of this massless particle are carrying enough energy to cook your skin, power entire cities, and illuminate galaxies on the far edge of the observable universe. This is the photon, the most fundamental object in existence, and after 4 centuries of obsessive study, the most mysterious thing physicists have ever tried to explain. It travels at exactly 299,792 kilometers per second, always, everywhere, in every reference frame. From the photon's perspective, time itself does not exist. Emission and absorption happen in the same instant, no matter whether it crosses a room or crosses 10 billion light-years of space. The universe, to a photon, is flat, instantaneous, timeless, and science has no comfortable way to reconcile that with the reality you and I experience. In 1605, Isaac Newton called light a stream of tiny corpuscles, invisible bullets flying through the void. By 1801, scientists proved he was wrong. Light was a wave, rippling through space like sound through air. Then, in 1905, Albert Einstein shattered that certainty and dragged physics into the quantum age by proving Newton was right all along. Sort of. Light is both. It is particle and wave, bullet and ripple, depending on how you look. And that duality, that impossible contradiction, has haunted every physicist since. This is the story of the photon, not the simple version you learnt in school, but the real one, the one that took humanity from candlelight to quantum field theory, the one that revealed the most accurate scientific framework ever constructed and still left us with questions we cannot answer. Because after everything we have learned, light remains what it has always been, a mystery dressed in mathematics, moving at the speed of forever. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Light moves at 300,000 kilometers per second. That number sits at the top of this video's title, and it's one of the most repeated figures in all of physics. You've probably heard it 1,000 times. You've probably nodded along, filed it away somewhere between the speed of sound and the distance to the moon, and moved on with your day. But here's the part nobody tells you when they rattle off that number like it's a fun fact at a dinner party. From the perspective of the thing actually doing the moving, the photon itself, no time passes at all. None. Zero. A photon emitted from the core of a distant star 10 billion years ago, and a photon that just bounced off the screen in front of your face right now, experienced exactly the same duration of travel, which is to say, they experienced nothing. For them, if a photon could be said to have a perspective, emission and absorption are the same event. The journey you measure in billions of years across billions of light years is to the photon instantaneous. It doesn't age, it doesn't wait, it doesn't experience the passage of time because time, from its point of view, does not exist. And that's where things stop making sense. We live in a universe where time is everything. You wake up, you age, you move through seconds and minutes and decades. Cause leads to effect. Events happen in sequence. You remember yesterday. You plan for tomorrow. Time is the stage on which literally everything in your life unfolds. And then there's light, the thing that lets you see all of it. And light doesn't participate. It moves through the universe at a fixed, unyielding, absolute speed. And in doing so, it steps outside the rules entirely. Albert Einstein figured this out in 1905, though he didn't start with photons. He started with a thought experiment he'd been chewing on since he was a teenager. What would it look like, he wondered, if you could ride alongside a beam of light, traveling at the same speed, keeping pace with it the way you might ride a bike next to a friend? If light is a wave, as physicists in the 1800s had proven beyond any doubt, then you should see it frozen in place, a stationary ripple in space, locked in time. But that didn't make sense. Waves don't freeze, they propagate, they move. A stationary wave isn't a wave at all, it's just a shape. Einstein couldn't shake the problem, and by the time he was working as a patent clerk in Bern, barely scraping by, no academic position, no institutional backing, no access to a lab, he'd realized something profound. The problem wasn't with the wave, the problem was with the assumption that time flows the same way for everyone. It doesn't. Time is not a universal metronome ticking away in the background while the universe does its thing. Time is relative. It depends on how fast you're moving. And if you're moving at the speed of light, time stops, not slows down, stops. That's what special relativity tells us. The faster you move through space, the slower you move through time. It's not a metaphor, it's not a philosophical musing. It's a measurable, testable, experimentally confirmed feature of reality. Put an atomic clock on a jet, fly it around the world, bring it back, and compare it to an identical clock that stayed on the ground. The one that flew will have ticked slightly slower. The difference is tiny, measured in billionths of a second, but it's there, real, repeatable. The clock didn't malfunction. Time itself passed more slowly for the clock in motion. Now scale that effect up. Keep accelerating. The closer you get to the speed of light, the more dramatic the effect becomes. At 90% the speed of light, time slows to less than half its normal rate. At 99%, it's running at about 14%. At 99.9%, you're down to about 4%. The curve gets steeper and steeper, bending toward an asymptote it can never quite reach. And at exactly 300,000 kilometers per second, the speed every photon in the universe travels, time dilation reaches infinity. Time stops completely. This is not a glitch in the math. It's what the math is telling you happens. A photon, by the rules of the universe it inhabits, does not experience time. It exists in a state where its emission and absorption, no matter how far apart they appear to us, are a single instantaneous event. And yet, here's the kicker. We measure the journey, we clock it. We know exactly how long it takes light to travel from the sun to Earth. 8 minutes and 20 seconds. We know how long it takes to cross the Milky Way. 100,000 years. We know the light reaching our telescopes from the edge of the observable universe has been traveling for more than 13 billion years. We measure all of it with exquisite precision. Time is passing for us. The photon just doesn't agree. That asymmetry is one of the strangest features of the universe. You and the photon are both participants in the same event, the photon's journey from point A to point B, but you experience it in completely different ways. For you, the journey takes time. For the photon, there is no journey. There's only a beginning and an end, collapsed into a single moment. It gets weirder. If a photon doesn't experience time, then from its perspective, the universe has no spatial extent in the direction it's traveling. Length contraction is the other half of special relativity, the partner to time dilation. As you accelerate toward the speed of light, distances in the direction of your motion appear to shrink. At the speed of light, they shrink to zero. A photon, emitted from a galaxy 10 billion light-years away, doesn't traverse 10 billion light-years of space. From its reference frame, that distance is zero. The galaxy and your eyeball, separated by an incomprehensible gulf of space and time from your perspective, are in the same place from the photons. Think about what that means for a second. Every photon in the universe, no matter where it came from, no matter where it's going, exists in a state where its entire journey is compressed into a single point in space-time. The Big Bang, if photons had been around to witness it, and the heat death of the universe trillions of years from now, if anything is left to emit light, are the same event. The photon doesn't traverse the timeline of the cosmos. It lives outside it. And this thing, this timeless traveler, this massless flicker of energy, is the only reason you can see anything at all. Light is the universe's messenger service. Every piece of visual information you have ever received, every image your brain has ever constructed, every color, every shadow, every reflection arrived on the back of a photon. The screen in front of you right now is emitting billions of them per second, each one carrying a tiny packet of energy tuned to a specific wavelength. Some of those photons hit your retina, get absorbed by cells at the back of your eye, trigger a cascade of electrical signals, and your brain interprets the result as an image. That process, the one happening right now as you read this, depends entirely on particles that do not experience time. Here's another way to think about it. The fastest anything in the universe can move is the speed of light. Not because light is special, but because the speed of light is actually the speed of causality. It's the speed at which cause and effect can propagate through space. If you flip a light switch, the signal telling the light to turn on travels down the wire at a significant fraction of the speed of light. If the sun exploded right now, we wouldn't know for 8 minutes because that's how long it takes light, or in this case the absence of it, to cross the distance. Information cannot move faster than light. The universe has a speed limit, and light is the thing traveling at that limit. But light doesn't have mass. That's critical. If photons had even the tiniest amount of rest mass, they couldn't travel at the speed of light. The equations of relativity make this clear. Accelerating an object with mass to the speed of light would require infinite energy. You can't do it. The universe won't let you. Photons bypass the restriction entirely by having no mass to accelerate in the first place. They don't speed up. They don't slow down. They're created already moving at 300,000 kilometers per second, and they stay at that speed until something absorbs them. Scientists have tested this. They've tested it so many times, with so much precision, that the current experimental upper limit for the photon's mass is absurdly small. Less than 1/1,000,000,000 of 1/1,000,000,000 of 1/1,000,000,000 of a kilogram. For all practical purposes, and according to every measurement we've ever made, the photon's rest mass is exactly zero, not approximately zero. Zero. And yet, despite having no mass, photons carry momentum. That sounds impossible. Momentum, the thing you learnt about in high school physics, is mass times velocity. No mass, no momentum. Except photons didn't get the memo. They have momentum. Real, measurable, physical momentum. Enough momentum to push things. You can build a solar sail, a giant reflective sheet in space, and the pressure from sunlight hitting it will slowly, gently, but very definitely accelerate a spacecraft. No fuel, no exhaust, just photons bouncing off a mirror. The momentum they carry is tiny, but it's real. And if you have enough photons, millions of them, billions of them, trillions of them streaming out from a star every second, that pressure adds up. This is not a theoretical curiosity. Light pressure is a real force. It's strong enough to shape the tails of comets, pushing dust and gas away from the sun into those long glowing trails we see in the night sky. It's strong enough that astronomers have to account for it when calculating the orbits of small asteroids near Earth. Photons don't just carry information, they exert force. So here's where we are. Photons have no mass. They don't experience time. They don't traverse space in the way you or I would understand it. And yet they carry energy, they carry momentum, they move at the absolute speed limit of the universe, and they are the only way anything in the cosmos can send a signal to anything else. What are they? Not metaphorically, not poetically, actually, physically, fundamentally, what is a photon? You can't hold one. You can't slow it down to get a good look. You can't put it in a jar and study it at your leisure. The instant a photon interacts with anything, a detector, a molecule, your eye, it gets absorbed. It stops being a photon. The thing you wanted to measure is gone, replaced by a small jolt of energy dumped into whatever absorbed it. Photons are the ultimate ephemeral object. They exist only in motion, only in transition, only in the act of traveling from one event to another. And the moment that trip ends, they cease to exist. This is the paradox at the heart of light. The thing is everywhere. It's the most common phenomenon in your daily experience. You're bathed in it. You depend on it. Your entire visual understanding of the world is built on it. And yet, when you ask what it actually is, the answer gets slippery. For most of human history, people didn't ask. Light was just light. The thing that let you see. The thing that came from the sun and fires and glowing coals. It illuminated, it warmed, it behaved in predictable ways. Shadows formed, reflections appeared in water. That was enough. Then someone asked a different kind of question. Not what does light do, but what is light made of? And that question, innocent as it sounds, opened a door nobody was ready to walk through. Isaac Newton thought light was made of tiny particles. He called them corpuscles, little bits of matter shot out from luminous objects like invisible bullets. The idea had a certain appeal. It explained why light traveled in straight lines. It explained reflections. Throw a ball at a wall and it bounces. Shoot a corpuscle at a mirror and same thing. Clean, simple, mechanical. Then someone else, a contemporary of Newton's, a man named Christian Huygens, suggested the opposite. Light, he said, wasn't particles, it was waves, ripples in some invisible medium, the way sound is ripples in air, and for a while nobody could decide who was right. Both ideas seemed to work. Both explained some things and struggled with others. The argument simmered for more than a century. And then, in the early 1800s, a British polymath named Thomas Young performed an experiment so simple, so elegant, that it settled the question, or so everyone thought. He shined light through two narrow slits and watched what appeared on a screen behind them. If light was made of particles, you'd expect two bright bars, one behind each slit. What he saw instead was a pattern of alternating light and dark bands, an interference pattern. The kind of pattern you only get from waves overlapping, reinforcing in some places, cancelling out in others. That was it. Light was a wave. Newton was wrong. Case closed. Physics moved on. Except it wasn't closed, because about 100 years after Young's experiment, another problem surfaced. This one had to do with how hot objects glow. Heat something up, a piece of iron, the filament in a light bulb, and it emits light. The hotter it gets, the more light it emits, and the color shifts from red to orange to white. Physicists tried to calculate how much light should be emitted at each color, each wavelength, using the wave theory of light. The math predicted something absurd. It said that any object, at any temperature, should emit an infinite amount of energy in the ultraviolet range. Infinite. Obviously, that doesn't happen. The prediction was so wrong, so catastrophically broken, that scientists gave it a name, the ultraviolet catastrophe. Max Planck fixed it in 1900 by suggesting something nobody wanted to hear. What if energy wasn't continuous? What if it came in tiny, discrete chunks? Quanta, that word, quantum, entered physics not as a bold new theory, but as a desperate patch to make the math work. And it did work. The ultraviolet catastrophe vanished, but the cost was steep. If energy came in chunks, then light, which carries energy, must come in chunks too. 5 years later, Einstein took that idea seriously. He proposed that light wasn't just waves. It was also particles, discrete packets of energy, quanta of light. He used the idea to explain something called the photoelectric effect, a phenomenon where light hitting a metal surface knocks electrons loose. The wave theory couldn't explain why only certain colors of light worked, why dim blue light could do it but bright red light couldn't. But if light came in packets, each packet carrying a specific amount of energy depending on its color, the whole thing made sense. Blue light packets carried more energy, red ones didn't. Simple. Einstein got the Nobel Prize for that work. Not for relativity, for figuring out that light, which everyone had finally agreed was a wave, was also somehow a particle. And that's where the real strangeness begins. Isaac Newton was not the first person to wonder what light was made of. That question is ancient, older than empires, older than written language in some forms. Someone, somewhere, probably sitting around a fire tens of thousands of years ago, watched the flames flicker and asked themselves why they could see it. What was traveling from the fire to their eyes? Was it something the fire sent out, or something the eye reached toward? Was light a thing, or was it an action? The ancient Greeks took their best guess. Euclid and Ptolemy thought vision worked by emission. The eye, they claimed, sent out invisible rays that touched objects and reported back. You didn't see the world, you felt it with beams of light shooting from your face. It sounds absurd now, but try to imagine the world without any of the tools we take for granted. No microscopes, no understanding of cells or nerves or electrical signals. You open your eyes and the world appears. Close them and it vanishes. What else would you conclude except that the eye itself was doing something active? Other Greek philosophers disagreed. Empedocles proposed that objects emitted tiny particles that flew into the eye. Democritus, the atomist, took it further. He believed everything, light included, was made of indivisible particles moving through empty space. Light was atoms, just a specific kind. Fast ones, small ones, the kind that slipped through the gaps in other matter and triggered the sensation of sight when they hit your eye. He was wrong about the mechanism, but the intuition that light might be made of discrete pieces wasn't a bad starting point. Then the question sat dormant for a very long time. The fall of Rome, the rise and fall of other empires, 1,000 years of human history where light was studied mostly for practical purposes. How to grind lenses, how to make better mirrors, how to improve vision with spectacles. What light was made of took a back seat to what you could do with it. René Descartes brought the question back in the 1600s. He thought light was a pressure transmitted through an invisible medium, the way sound is transmitted through air. Press on one end of the medium and the disturbance propagates instantly to the other side. No particles flying through space, no delay, just instantaneous action at a distance. It was wrong, but it was rigorous. Descartes tried to build a mechanical model of the universe, and light fit into that model as a kind of push, a tendency, a pressure wave in an all-pervading substance he called the plenum. Then came Newton. Isaac Newton was 23 years old in 1666 when the University of Cambridge closed due to an outbreak of the plague. He went home to the family farm in Woolsthorpe, Lincolnshire, and spent the next 2 years thinking. No classes, no distractions, no colleagues stopping by his office to chat. Just Newton alone, with time to work through the problems that had been nagging him. During those 2 years, he invented calculus, formulated the laws of motion and universal gravitation, and began the experiments on light that would eventually dismantle centuries of assumptions about color and vision. History calls it his annus mirabilis, his miracle year. Technically, it was more like 18 months, but who's counting? Newton's first significant experiment with light was deceptively simple. He took a glass prism, the kind you might find in a novelty shop today, and placed it in a darkened room. He let a narrow beam of sunlight pass through a small hole in the window shutter, hit the prism, and project onto the far wall. What appeared was a spectrum, a band of colors stretching from red on one end to violet on the other. This wasn't new. People had been playing with prisms for decades. What was new was what Newton did next. He didn't assume the prism was creating the colors. That was the prevailing theory at the time. Glass, people thought, modified white light, corrupting it somehow into colors the way a stain spreads through cloth. Newton suspected otherwise. He tested it by taking a second prism and placing it in the path of one of the colored beams. If the first prism had corrupted the light, the second prism should corrupt it further, shifting the color again. It didn't. Red light stayed red, blue stayed blue. The colors were not created by the prism, they were separated by it. White light, Newton concluded, was not pure. It was a mixture, a combination of all the colors blended together. The prism wasn't adding anything. It was just spreading them out, bending each color by a different amount because each color, Newton realized, had different properties. This was revolutionary. It overturned centuries of belief that white light was fundamental and colors were degradations of it. Newton showed the opposite. Colors were fundamental. White was the mixture. He published his findings in 1672 in a paper sent to the Royal Society, and the reaction was mixed. Some praised it. Others, including Robert Hooke, one of the most prominent scientists in England at the time, attacked it. The criticism stung. Newton was young, relatively unknown, and not particularly interested in public fights. He withdrew from the debate and spent years refining his ideas in private. By the time he finally published Optics in 1704, more than 3 decades after that first paper, Newton had developed a comprehensive theory of light. And at the center of that theory was a radical claim. Light, he proposed, was made of particles, tiny, discrete, luminous corpuscles emitted by glowing objects and traveling in straight lines through space. They were not atoms in the modern sense. Newton didn't think they had mass the way ordinary matter did, but they were things, objects, entities with properties, with momentum, with the ability to exert force and be acted upon by force. Why did Newton think this? Part of it was philosophical. The worldview of the 1600s was deeply mechanical. Descartes had framed the universe as a giant machine, all gears and levers and pushes and pulls. Newton, despite his many disagreements with Descartes, shared that mechanical intuition. If light could push on things, and it could, you could see it in the way sunlight warmed your skin, then light had to be made of something. Waves, in Newton's view, were too vague, too abstract. Particles were concrete. You could imagine them. You could calculate their trajectories. Part of it was also observational. Light travels in straight lines. You see this every day. Shadows have sharp edges. If you block a light source with your hand, the shadow on the wall matches the shape of your hand. If light were a wave, Newton reasoned, it should bend around obstacles the way sound does. You can hear someone talking around a corner, but you can't see them unless you have a direct line of sight. Waves diffract. Light, as far as Newton could tell, did not. Particles, on the other hand, travel in straight lines unless something deflects them. Shoot a musket ball and it flies straight until it hits something or gravity pulls it down. Shoot a corpuscle of light and same thing. Straight line, predictable path. Newton also thought the particle theory explained reflection better than any wave theory could. When light hits a mirror, it bounces off at the same angle it came in. That's the law of reflection, known since ancient times. If light is made of particles, reflection is just a collision. A ball thrown at a wall bounces back. A corpuscle hitting a polished surface does the same. Clean, simple, mechanical. Refraction, the bending of light when it passes from air into water or glass, was trickier. Newton proposed that the corpuscles were attracted to the denser medium, pulled slightly toward it as they crossed the boundary, which changed their direction. It wasn't a perfect explanation. The math got messy, but it worked well enough to account for the observations, and that was what mattered. The bigger problem was color. If light was made of particles, and white light was a mixture of colors, then each color had to correspond to a different type of particle. Red corpuscles, orange corpuscles, yellow, green, blue, violet, each one with its own properties. Red light bent less than violet light when passing through a prism, so red corpuscles had to be larger or heavier or somehow less susceptible to the forces acting on them. Newton didn't specify the details. He left the mechanics vague, but the implication was clear. There wasn't just one kind of light particle. There were several, maybe dozens, each tuned to a different color. This is where Newton's theory starts to feel less like physics and more like taxonomy. He was cataloging particles the way a biologist might catalog beetles. Red ones, blue ones, shiny ones, dull ones. It worked as a descriptive framework, but it didn't explain why. Why did red corpuscles bend less than blue ones? What made them different? Newton didn't have an answer. He didn't pretend to. In optics, he wrote openly about the limits of his knowledge. He proposed the corpuscular theory not as a final truth, but as the best available explanation given the evidence. He was careful, cautious, aware that future experiments might overturn him. They did, but not for more than a century. Newton's influence in physics was so overwhelming that his corpuscular theory became the default view of light for generations. It wasn't that other scientists couldn't imagine alternatives. It was that arguing with Newton, even after his death in 1727, felt like arguing with gravity. The man had rewritten the rules of the cosmos. He'd explained planetary motion, tides, the shape of the Earth. If Newton said light was made of particles, who were you to disagree? There was one person willing to disagree. Christian Huygens, a Dutch mathematician and physicist, published his own theory of light in 1690, 14 years before Newton's optics came out. Huygens proposed the opposite. Light, he said, was not particles, it was waves. Pulses propagating through an invisible medium he called the aether, a substance that filled all of space and allowed light to travel the way air allows sound to travel. Every point touched by a wave becomes the source of a new wave, spreading outward in all directions. Add up all those little waves and you get the overall behavior of light. Reflection, refraction, all of it could be explained by waves interfering with each other, reinforcing in some places, cancelling in others. Huygens' theory was elegant. It explained a lot, but it had problems. For one thing, it required the aether, and nobody could detect the aether. Nobody could measure it, weigh it, or explain why it didn't slow down the planets as they moved through it. For another, Huygens couldn't explain polarization, a phenomenon where light behaves differently depending on its orientation. Newton's particle theory struggled with polarization too, but at least particles were tangible. You could imagine them spinning or tumbling as they flew through space. Waves in the aether didn't give you that flexibility. So the debate sat there. Particles versus waves, Newton versus Huygens. And because Newton was Newton, his version won by default. The Royal Society in London favoured particles. The French Académie des Sciences leaned toward waves, partly because they were French and therefore inclined to take the opposite position from the English on general principle. But in England, where most of the influential experimental work was being done, corpuscles reigned. What's fascinating about this period is how little experimental evidence actually separated the two theories. Both explained the same phenomena, both made similar predictions. The choice between them came down to intuition, to philosophy, to which mental picture felt more satisfying. Do you like the idea of light as a thing, a stream of tiny bullets zipping through the void? Or do you prefer light as a disturbance, a ripple in an invisible ocean? Your answer said more about your worldview than it did about the evidence. Newton himself never claimed absolute certainty. In optics, he included a series of questions at the end, a list of open problems he hoped future scientists would solve. Are light corpuscles all the same size? Do they have mass? Can they be split into smaller pieces? What happens to them when they're absorbed? He didn't know. He admitted he didn't know. The corpuscular theory was a framework, not a finished product. It organized the data, made testable predictions, and gave experimentalists something concrete to work with. That was enough, and it was enough for a long time. Through the 1700s and into the early 1800s, Newton's particle theory remained the standard explanation for light. Textbooks taught it, professors lectured on it, experimentalists designed their work around it. The universe, as far as anyone could tell, was made of matter and forces, particles and pushes. Light fit neatly into that picture as just another kind of particle, maybe a bit unusual, but nothing fundamentally strange. Then in 1801, a British polymath named Thomas Young performed an experiment that would shatter that picture completely. He didn't set out to overthrow Newton. He was just curious about interference patterns, the way ripples on water overlap and create regions of calm and regions of chaos. He wondered if light might do the same thing. So he shined a beam of sunlight through two narrow slits cut into a piece of card and watched what appeared on a screen behind them. If light was made of particles, you'd expect two bright lines on the screen, one behind each slit. Some corpuscles go through the left slit, some through the right, and they pile up in two separate spots. That's what particles do. That's what Newton's theory predicted. Young saw something else entirely. Instead of two lines, he saw dozens, alternating bright and dark bands stretching across the screen, an interference pattern, the kind of pattern you only get when waves overlap. Where the peaks of two waves meet, they reinforce. Bright band. Where a peak meets a trough, they cancel. Dark band. The pattern Young observed was unmistakable. Light was behaving like a wave. The result was controversial. Newton's supporters dismissed it. They argued that Young's slits were too crude, that he had introduced errors, that the effect was some kind of artifact. Young defended his work, but he didn't have Newton's stature. He was a medical doctor, a linguist, a man who dabbled in a dozen fields. He wasn't a towering figure of physics. His experiment was noted, debated, and then largely ignored. The particle theory held. It took another generation for the wave theory to gain serious traction. Augustin Jean Fresnel, a French engineer, repeated Young's experiment with better equipment and more rigorous analysis in the 1810s. He not only confirmed the interference pattern, he developed the mathematics to predict it. He showed that if you treated light as a wave, you could calculate exactly where the bright and dark bands would appear, and the calculations matched the observations perfectly. By the 1820s, the wave theory had won. Light was not particles, it was waves. Newton, for the first time in more than a century, was wrong, except he wasn't. Not entirely. because 70 years later the wave theory would run into its own catastrophic failure, and the particle idea would come roaring back, stronger and stranger than Newton ever imagined. The problem with being right for 100 years is that when you're finally proven wrong, the correction doesn't come gently, it comes like a hammer. By the early 1800s, Isaac Newton had been dead for nearly 8 decades, but his corpuscular theory of light still dominated physics. It wasn't just accepted, it was canon. Textbooks taught it. Universities built curricula around it. The particle model explained reflection. It explained refraction. It explained why shadows had sharp edges. And more importantly, it bore the name Newton. Arguing against it felt less like scientific debate and more like heresy. You didn't question Newton. You built on Newton. You refined Newton. You didn't tear him down. Christian Huygens had tried. Back in 1678, more than 2 decades before Newton published Optics, Huygens had written Traité de la Lumière, Treatise on Light, and in it he'd laid out a completely different vision. Light, he proposed, was not made of particles. It was a wave, a disturbance propagating through an invisible medium that filled all of space, something he called the luminiferous aether. Every point that a wave touched became the source of a new wavelet, spreading outward in all directions like ripples on a pond. Add up all those wavelets, and you got the overall motion of light. Reflection happened when waves bounced off a surface. Refraction happened when waves slowed down, entering a denser medium, bending their path the way ocean waves bend when they approach a shallow beach. It was elegant. It was mathematically rigorous, and it was almost completely ignored. Part of the problem was timing. Huygens published his wave theory in 1690, right in the middle of Newton's rise to dominance. By then, Newton had already explained planetary motion, derived the law of universal gravitation, and was in the process of reshaping physics into something unrecognizable from what had come before. Huygens was brilliant, no question, but he wasn't Newton, and when the two men disagreed, the scientific community picked a side. They picked Newton. The other problem was the aether itself. Huygens needed it. Waves don't propagate through nothing. Sound waves move through air. Water waves move through water. If light was a wave, it had to be waving in something. The aether was that something. An invisible, weightless, frictionless substance that permeated every corner of the universe, filling the space between stars, between planets, between the atoms in your body. It let light travel, but it didn't slow down the planets. It didn't create drag. It didn't interact with matter in any way you could measure. It was there, Huygens assured everyone, even though nobody could detect it. That was a hard sell. Scientists in the 1600s were deeply skeptical of invisible substances. Descartes had filled the universe with invisible fluids and vortices, and Newton had spent years tearing that framework apart. The idea that you needed another invisible medium to explain light felt like a step backward. Particles didn't need a medium, they just flew through empty space. Simple, clean, no metaphysical baggage. So Huygens' wave theory was noted, filed away, and largely forgotten. The corpuscular model rolled on unchallenged for over a century, and then Thomas Young walked into the room. Young was not your typical physicist. Born in 1773 in Somerset, England, he was a polymath in the truest sense of the word. By the time he was 14, he'd taught himself a dozen languages, including Latin, Greek, Hebrew, Arabic, and Persian. He studied medicine at the universities of London, Edinburgh, and Göttingen, earning his degree before he turned 21. He practiced as a physician in London, lectured on natural philosophy at the Royal Institution, contributed to the decipherment of Egyptian hieroglyphics, and somewhere in between all of that, he decided to settle the question of what light actually was. Young didn't start with a plan to overthrow Newton. He was curious. He'd been reading about sound waves, about how two sounds could combine to create silence if their peaks and troughs lined up just right. Destructive interference, it was called. He wondered if light might behave the same way. If light was a wave, as Huygens had claimed, then two beams of light overlapping should interfere with each other. In some places they'd reinforce. Brighter light. In other places they'd cancel. Darkness. That was the prediction. And if he could demonstrate it, he'd have proof. In 1801, Young set up an experiment at the Royal Institution. He took a beam of sunlight, passed it through a single narrow slit to make it coherent, then let that light hit a second barrier with two slits cut close together. The light passing through those two slits spread out and overlapped on a screen behind them. If light was made of particles, you'd expect two bright spots on the screen, one behind each slit. Some particles go left, some go right. They hit the screen, done. That's not what appeared. Instead, Young saw a series of bright and dark bands stretching across the screen. Stripes. A dozen or more, alternating light and dark, with the brightest band right in the center where you'd expect the two beams to overlap most strongly. It was an interference pattern, unmistakable. The kind of pattern you only get when waves meet and either add together or cancel out. Light from the left slit and light from the right slit were arriving at the screen at the same time, and depending on whether their peaks aligned or their peaks met troughs, you got brightness or darkness. Young wasn't just seeing waves, he was seeing proof. Light behaved exactly the way water ripples behave when they pass through two gaps in a barrier. Drop two stones in a pond close together and watch the ripples spread. Where the ripples meet, they form a pattern, alternating regions of high water and calm water. Young had just done the same thing with light. He presented his results to the Royal Society in 1803. The reaction was mixed. Some scientists were intrigued, others were hostile. Henry Brougham, a lawyer and science commentator, wrote a scathing anonymous review in the Edinburgh Review, accusing Young of arrogance, of misunderstanding basic optics, of wasting everyone's time with an experiment that proved nothing. The review was so harsh that Young largely withdrew from public scientific debate for years. He kept working, kept refining his ideas, but he stopped trying to convince people. He'd shown them the interference pattern. If they didn't want to see it, that was their problem. The resistance wasn't purely intellectual, it was cultural. Newton's particle theory wasn't just a scientific model, it was a pillar of British identity. Newton was a national hero, the man who'd put England at the center of the scientific revolution. To suggest he was wrong about light felt, to many of his countrymen, like betraying the legacy. The French, on the other hand, had no such loyalty. They'd been skeptical of Newton's particles from the start, partly because Descartes had primed them to think in terms of waves and fluids, and partly because they enjoyed disagreeing with the English on principle. Enter Augustin Jean Fresnel. Born in 1788 in Normandy, Fresnel was a civil engineer by training, not a physicist. He worked for the French government building roads and bridges, but in his spare time he studied optics. He'd read Huygens, he'd read Young, and he believed they were onto something. In 1815, during a brief period of political exile, he deposed Napoleon's return during the 100 Days. Fresnel found himself with time on his hands and a lot of questions about how light actually worked. He started running his own experiments on diffraction, the bending of light around obstacles. He discovered that when light passed through a narrow opening or grazed the edge of an object, it spread out in a way that particles simply couldn't explain, but waves could. Fresnel didn't just observe diffraction, he mathematized it. He developed a set of equations now called Fresnel integrals that could predict exactly how light would spread, exactly where the bright and dark fringes would appear, down to fractions of a millimeter. He treated light as a wave and calculated what that wave should do under different conditions, and every time his predictions matched the experimental results perfectly. In 1819, the French Académie des Sciences announced a prize for the best explanation of diffraction. Fresnel submitted his wave theory. The judging committee included some of the most prominent scientists in France, and one of them, Siméon Denis Poisson, was deeply skeptical. Poisson ran through Fresnel's equations and found what he thought was a fatal flaw. According to Fresnel's math, if you placed a small opaque disk in a beam of light, the wave theory predicted a bright spot should appear in the center of the shadow directly behind the disk. That was absurd. Everyone knew shadows were dark. Poisson presented this as a reductio ad absurdum, proof that Fresnel's theory had to be wrong. François Arago, the head of the committee, decided to test it. He set up the experiment. He placed a small metal disc in a light beam and looked at the shadow on a screen behind it. There, right in the center of the shadow, exactly where Poisson said it couldn't be, was a bright spot, a tiny pinprick of light surrounded by darkness. The spot is still called the Arago spot today, though some call it Poisson's spot in honor of the man who accidentally predicted it while trying to disprove the theory that explained it. Fresnel won the prize. His wave theory was published, refined, and within a decade, it became the accepted explanation for light across Europe, not just in France, everywhere. The interference patterns, the diffraction effects, the mathematical predictions, all of it lined up too neatly to ignore. By the 1830s, the particle theory was dead. Light was a wave. The question was settled. But settled left a problem. Waves need a medium. Sound waves need air. Water waves need water. Light waves need what? The luminiferous aether was back on the table, and now it wasn't optional. If light was a wave, the aether had to exist. Scientists couldn't see it, couldn't touch it, couldn't measure it directly, but the math required it, so they accepted it. They built models of it. They speculated about its properties. The aether became the central mystery of 19th century physics. What was it made of? How did it transmit waves? Why didn't it slow down the planets? Nobody had good answers. But the wave theory worked so well for explaining everything else about light that physicists were willing to live with the mystery for a while. Then in the 1860s, a Scottish physicist named James Clerk Maxwell did something that changed everything. He wasn't trying to explain light. He was trying to understand electricity and magnetism. For decades, scientists had known the two were related. Moving a magnet near a wire created an electric current. Running a current through a wire created a magnetic field, but nobody knew why. The phenomena were catalogued, measured, repeatable, but the underlying connection was missing. Maxwell thought the connection might be mathematical. He took the experimental results of Michael Faraday, Hans Christian Ørsted, André-Marie Ampère, and others, and tried to unify them into a single coherent framework. He wrote down a set of equations, just 4 of them, that described how electric and magnetic fields behave and how they interact. The equations were elegant, symmetrical, and they did something unexpected. They predicted waves. If you disturbed an electric field, the equation said it would create a changing magnetic field. That changing magnetic field would create a changing electric field. That new electric field would create another magnetic field, and so on. The disturbance would propagate outward as a self-sustaining wave, an oscillation of electric and magnetic fields rolling through space. And Maxwell could calculate how fast that wave should travel. He plugged in the known values for the electric and magnetic constants. numbers that had been measured in labs with wires and magnets and batteries, and he got a speed, roughly 310 million meters per second. That number looked familiar. The speed of light, measured by Hippolyte Fizeau and Léon Foucault just a few years earlier, was about 300 million meters per second. The match was too close to be a coincidence. Maxwell stared at his equations and realized what they were telling him. Light wasn't just similar to an electromagnetic wave. Light was an electromagnetic wave. Visible light was a ripple in the electric and magnetic fields, the same fields that made compasses point north and sparks jump between metal electrodes. He published his findings in 1865 in a paper titled A Dynamical Theory of the Electromagnetic Field. In it he wrote, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena." He didn't just unify light with electromagnetism. He predicted that other kinds of electromagnetic waves should exist, waves with longer wavelengths than visible light, and waves with shorter wavelengths, stretching out in both directions. We call them radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. Maxwell predicted the entire electromagnetic spectrum decades before most of it was discovered, just by working through the math. The impact was staggering. Light wasn't some separate phenomenon, some special case that needed its own rules. It was part of a larger picture. Electricity, magnetism, and light were all manifestations of the same underlying fields, governed by the same equations, and those equations predicted waves, not particles, waves. Maxwell's work didn't just confirm the wave theory of light, it elevated it. The wave model had been built on observations, interference patterns, diffraction experiments, clever measurements. Maxwell gave it a foundation. He showed why light was a wave, what it was waving in, sort of. The ether was still there, lurking in the background. Maxwell's equations described how electromagnetic waves propagated, but they didn't explain what the fields themselves were made of. They didn't say what was actually oscillating. The ether remained a necessary assumption, the invisible stage on which the electromagnetic drama played out. For the next few decades, physicists tried to nail down the ether's properties. They assumed it was a solid, because transverse waves, the kind of waves light seemed to be, only propagate through solids, not fluids. But if it was solid, it had to be incredibly rigid to support waves moving at the speed of light. Stiffer than steel, stiffer than diamond, and yet somehow it offered no resistance to objects moving through it. The Earth plowed through the ether at 30 kilometers per second as it orbited the Sun, and the ether didn't slow it down at all. It was a substance that behaved like the most rigid solid ever conceived, and the most yielding fluid at the same time. The contradictions piled up. Experiments tried to detect the ether directly, to measure the Earth's motion through it. The most famous attempt came in 1887 when Albert Michelson and Edward Morley built an interferometer sensitive enough to detect tiny shifts in the speed of light caused by the Earth's motion through the ether. They found nothing, no shift, no variation. Light moved at the same speed in every direction, regardless of how the Earth was moving. The result was baffling. If the ether existed, the experiment should have detected it. It didn't. The wave theory was still right. The math worked. The predictions matched the experiments. But the medium the waves were supposed to be traveling through was refusing to show up. Physicists were stuck with a model that explained everything about light except what light actually was. The ether became a ghost, essential to the theory but invisible to every test designed to find it. Still, by the 1890s, the wave model felt like the final word. Physics textbooks described light as electromagnetic waves. University courses taught Maxwell's equations. The interference patterns, the diffraction effects, the unification with electricity and magnetism, it all fit together too perfectly. The particle theory was a historical footnote, a dead-end Newton had wandered down before better experiments set everyone straight. Light was waves. That was the consensus, the foundation, the bedrock on which all of optics and electromagnetism stood. And then, in 1900, Max Planck found a crack in that bedrock. He didn't mean to. He was trying to solve a specific technical problem about how hot objects glow, a problem called blackbody radiation. The wave theory of light predicted that any object at any temperature should emit an infinite amount of energy in the ultraviolet range. Infinite. Obviously, that didn't happen. The prediction was so catastrophically wrong that physicists called it the ultraviolet catastrophe. Planck fixed the math by making a strange assumption. He assumed that energy couldn't be emitted continuously. It had to come in discrete chunks, little packets he called quanta. The size of each packet depended on the frequency of the light. Higher frequency, bigger packet; lower frequency, smaller packet. It was a trick, a mathematical patch. Planck didn't believe energy was actually quantized. He thought he was just smoothing over a rough spot in the equations, but the patch worked. The ultraviolet catastrophe disappeared. The predictions matched the experimental data perfectly, and buried in that fix was an idea that would unravel everything physicists thought they knew about light. 5 years later, Albert Einstein took Planck's quanta seriously. He proposed that light didn't just emit energy in packets. Light itself came in packets, discrete, indivisible chunks of energy, not waves, particles. He called them light quanta. Later, they'd be called photons. Einstein used the idea to explain the photoelectric effect, a phenomenon where light hitting a metal surface knocks electrons loose. The wave theory couldn't explain why only certain colors of light worked, why dim blue light could do it but bright red light couldn't. But if light came in packets, each packet carrying a specific amount of energy depending on its frequency, the whole thing made sense. Blue light packets carried more energy than red ones. Hit the metal with a blue packet and it had enough energy to kick an electron free. Hit it with a red packet and it didn't. Simple. Einstein got the Nobel Prize for that work in 1921. Not for relativity, for figuring out that light, which everyone had finally agreed was a wave, was also somehow a particle. And just like that, the question was open again. 100 years of experiments, a century of evidence, Maxwell's equations, the entire edifice of wave optics, and now particles were back on the table. Not Newton's corpuscles, something stranger, something that didn't replace the wave theory but sat next to it, incompatible and undeniable. The universe, it turned out, hadn't given physicists a final answer. It had given them a paradox, and the resolution to that paradox would require rethinking everything. By 1900, physics had won. Not just partially, not just mostly, completely. The universe had been mapped, explained, and packaged into a set of laws so elegant that some scientists were beginning to wonder if there was anything left to discover. Isaac Newton had explained motion and gravity. James Clerk Maxwell had unified electricity, magnetism, and light. Thermodynamics had figured out heat and energy. Mechanics, optics, electromagnetism, it all worked. Every prediction matched every measurement. The gaps were shrinking. The mysteries were getting solved. Lord Kelvin, one of the most prominent physicists of the era, reportedly said there were only 2 small clouds darkening the otherwise clear sky of physics. 2 tiny problems left to mop up. After that, physics would be done, finished, a completed science. He was catastrophically wrong. Those 2 clouds weren't minor issues. They were Category 5 hurricanes hiding just over the horizon, and they were about to obliterate everything physicists thought they understood. One of them would become quantum mechanics, the other would become relativity. And the man who lit the fuse on the first explosion was not Lord Kelvin, not any of the established giants of European science. It was a 26-year-old patent clerk working in Bern, Switzerland, who spent his days reviewing applications for electrical devices and his evenings rewriting the rules of reality. The crisis started with something mundane: glowing metal. Heat something up, an iron poker, the filament in a light bulb, a piece of charcoal, and it glows. The hotter it gets, the brighter it glows, and the color shifts. Red at lower temperatures, orange, yellow, white, and if you could keep heating it, blue. The relationship between temperature and the color of emitted light had been studied for decades. It was practical knowledge. Blacksmiths used it to judge the temperature of iron. Astronomers used it to estimate the temperature of stars. By the late 1800s, physicists wanted to understand the mechanism. What exactly was happening inside a hot object that made it emit light? They called it black-body radiation. A black body is an idealized object that absorbs all light that hits it and emits light based purely on its temperature. It doesn't reflect anything. It doesn't have any special material properties that skew the results. It's a theoretical construct, but you can approximate it pretty well with a small hole in the side of a heated enclosure. Radiation goes in, bounces around inside, and eventually some of it comes back out through the hole. Measure the spectrum of that radiation and you've got a black body spectrum. The measurements were clean, the data was solid. The problem was that nobody could explain it. Physicists tried using classical physics, the wave theory of light, Maxwell's equations, thermodynamics, everything in the toolkit. They wrote down equations predicting how much energy a black body should emit at each wavelength. The equations worked beautifully for long wavelengths, infrared and red light. But as you moved towards shorter wavelengths, blue, violet, ultraviolet, the predictions went completely off the rails. The math said that any object at any temperature should emit infinite energy in the ultraviolet range. Infinite. A glowing piece of metal, according to classical physics, should output more energy than exists in the universe. Obviously, that doesn't happen. You can hold your hand near a hot piece of iron and feel warmth. You don't get vaporized by an infinite blast of ultraviolet radiation. The prediction was so absurdly wrong that physicists gave it a name: the ultraviolet catastrophe. It wasn't just a small error, a rounding mistake you could paper over with better measurements. It was a fundamental failure. Classical physics, the entire framework built over 2 centuries of careful work, could not explain why a hot object glows the way it does. The theory predicted nonsense. Reality did something else, and nobody knew why. Max Planck knew the problem intimately. Born in Kiel, Germany in 1858, Planck was a theoretical physicist who had spent years working on thermodynamics. By 1899, he was a professor at the University of Berlin and deeply involved in the black-body radiation puzzle. He had access to the best experimental data available, measurements taken by his colleagues at the Physikalische Technische Reichsanstalt, Germany's national laboratory for precision measurement. The data was exquisite. Curves showing exactly how much energy was emitted at each wavelength for objects at different temperatures. The measurements were right, the classical theory was wrong. Planck's job was to fix it. He tried everything. He started with classical assumptions, waves, continuous energy, Maxwell's equations, and worked through the math over and over, looking for a way to make the predictions match the data. Nothing worked. The ultraviolet catastrophe kept showing up like a stubborn stain. Finally, in October 1900, Planck tried something desperate. He made an assumption he didn't believe, an assumption that violated everything classical physics said about energy. He assumed energy wasn't continuous. He assumed it came in discrete chunks, packets, quanta. The idea was radical. Energy in classical physics is smooth. You can have 1 joule, half a joule, a tenth of a joule, any fraction you want. It's like pouring water. You can pour as much or as little as you need. Planck's assumption said no, energy is more like coins. You can have 1 coin, 2 coins, 3 coins, but you can't have half a coin. The smallest unit of energy Planck proposed was tied to the frequency of the light. The higher the frequency, the bigger the chunk. He wrote it as E equals n times h times nu, where E is energy, n is an integer, nu is the frequency, and h is a new constant, a number Planck had to introduce to make the math work. Today we call it Planck's constant. Its value is about 6.626 times 10 to the negative 34th joule seconds, absurdly small. So small that for most everyday purposes energy looks continuous. But at the level of atoms and radiation, that tiny number matters. Planck plugged his quantized energy assumption into the blackbody equations, and everything clicked into place. The ultraviolet catastrophe vanished. The predictions matched the experimental data perfectly across the entire spectrum, from infrared to ultraviolet. It worked, but Planck didn't believe it. He thought he'd found a mathematical trick, a clever bit of bookkeeping that smoothed over a rough spot in the equations. He assumed that once someone smarter came along and figured out the real reason the math worked, the quanta would go away. Energy was continuous. It had to be. The universe couldn't actually work this way, could it? He presented his results in December 1900 to the German Physical Society. The paper was titled On the Theory of the Energy Distribution Law of the Normal Spectrum. Dry title, revolutionary content. Physicists noticed. Some were impressed by how well the formula fit the data. Others were skeptical. The assumption of quantized energy felt arbitrary, pulled out of thin air to fix a problem. There was no physical justification, no deeper principle underlying it. Planck himself admitted as much. He called it an act of desperation. But the formula worked, and that was enough to keep people talking. For 5 years, Planck's quantization sat there, a strange mathematical curiosity that solved one specific problem but didn't seem to connect to anything else. Physicists used the formula. They didn't take the quanta seriously. Energy was still continuous as far as anyone was concerned. And then in March 1905, a paper appeared in Annalender Physik, Volume 17, pages 132 to 148. The title was On a Heuristic Point of View Concerning the Production and Transformation of Light. The author was Albert Einstein, and the paper didn't just use Planck's idea, it took it seriously, deadly seriously. Einstein proposed something nobody was ready to hear. Light itself, not just the energy exchanged between light and matter, but light itself was made of discrete packets, quanta, particles. Einstein was 26 years old. He had no academic position, no laboratory, no access to experimental equipment. He worked at the Swiss Federal Patent Office in Bern, reviewing applications for electrical devices, dynamos and motors. He'd finished his PhD the previous year at the University of Zurich, with a dissertation so unremarkable that it barely got noticed. By every conventional measure, he was nobody. A junior bureaucrat with a physics degree, no connections, no reputation, no reason for anyone in the scientific establishment to pay attention to him, and in 1905 he published 4 papers that changed the universe, literally. One explained Brownian motion and provided the first solid evidence that atoms were real. One introduced the special theory of relativity, collapsing space and time into a single flexible fabric. One derived E equals mc squared, proving that mass and energy were interchangeable, and one, the paper on light quanta, shattered the wave theory of light and kicked off the quantum revolution. Historians call it his annus mirabilis, miracle year. 4 papers, any one of which would have been enough to earn a Nobel Prize under normal circumstances. He wrote all of them alone. No collaborators, no team, just Einstein, working nights after his day job, scribbling equations in a rented apartment. The light quanta paper wasn't even the one he thought was most important. He was prouder of the relativity work. But the light quanta paper was the one that scared people, because if Einstein was right and light was made of particles, then the entire wave theory, a century of experiments, Maxwell's equations, all of it, was incomplete at best and wrong at worst. Einstein's argument started with a problem called the photoelectric effect. The phenomenon had been discovered in 1887 by Heinrich Hertz, the same physicist who first detected radio waves. Hertz was running experiments with spark gap transmitters when he noticed something odd. When ultraviolet light shone on a metal surface, it made the metal emit electrons. Shine the light, electrons come out. Turn the light off, they stop. Simple enough, but the details didn't make sense. Classical physics, the wave theory of light, said light is energy spread out over a wave. The brighter the light, the more energy hitting the surface, the more vigorously the electrons should be ejected. Dim light should eject electrons weakly. Bright light should eject them strongly. That's not what happened. In experiments, the energy of the ejected electrons didn't depend on the brightness of the light. It depended on the color. Blue light ejected electrons with high energy. Red light ejected them with low energy. Dim blue light worked just as well as bright blue light. Bright red light, no matter how intense you made it, didn't work at all. It was as if the electrons were counting the frequency of the light and ignoring the intensity completely. Wave theory couldn't explain that. If light is a wave, energy should accumulate over time. Shine dim red light on a metal surface long enough, and eventually enough energy should build up to kick an electron free. That didn't happen. Either the electron came out immediately, within a fraction of a second, or it didn't come out at all. There was a threshold, a cutoff frequency. Below that frequency, no amount of light, no matter how bright, would do anything. Above that frequency, even a faint beam worked instantly. Einstein's explanation was brutal in its simplicity. Light, he said, is not a continuous wave. It's made of particles, discrete packets of energy. Each packet, each quantum, carries an energy equal to Planck's constant times the frequency, E equals h nu. When light hits a metal surface, it doesn't spread its energy around. One quantum interacts with one electron, all or nothing. If the quantum carries enough energy to overcome the electron's binding to the metal, the electron gets ejected. If it doesn't, nothing happens. Brightness, intensity, that just tells you how many quanta are hitting the surface per second. More quanta, more electrons ejected, but each electron gets its energy from a single quantum. The process is discrete, lumpy, particle-like. The hypothesis explained everything: why only certain colors worked, why the energy of the ejected electrons depended on frequency, not intensity, why there was a threshold, why the effect was instantaneous. It all fell out naturally if you treated light as quanta. Einstein even wrote down the equation. The maximum kinetic energy of an ejected electron equals h times nu minus the work function, where the work function is the minimum energy needed to free an electron from the metal. Simple, testable, radical. Einstein knew how radical it was. In the paper he wrote, "It seems to me that the observations on blackbody radiation, photoluminescence, the production of cathode rays by ultraviolet light, and other phenomena involving the emission or conversion of light can be better understood if one assumes that the energy of light is distributed discontinuously in space. The energy of a light ray spreading out from a point source is not continuously distributed over an increasing volume, but consists of a finite number of energy quanta which are localized at points in space, which move without dividing, and which can only be produced and absorbed as complete units. Read that again. Light is not continuously distributed. It consists of a finite number of energy quanta, localized at points, move without dividing, can only be produced and absorbed as complete units. Einstein wasn't hedging. He wasn't saying light sometimes behaves like particles under certain conditions. He was saying light is made of particles, discrete, indivisible, localized particles. He called them Lichtquanten, light quanta. The word photon wouldn't be coined until 1926 by an American chemist named Gilbert Lewis, and even then it didn't catch on immediately. Einstein himself never used the term, but the idea, that was Einstein's, and it was terrifying. The reaction from the physics community was not enthusiasm, it was horror. Max Planck, the man who had introduced quantization in the first place, rejected Einstein's hypothesis outright. Planck thought quantization was a property of matter, of how atoms emit and absorb energy, not a property of light itself. Light was still a wave. It had to be. Hendrik Lorentz, one of the leading experts on electromagnetism, called Einstein's light quanta dangerous and speculative. Even after Einstein published the paper, even after it started getting discussed at conferences, most physicists dismissed it. The wave theory was too successful, too well established. Maxwell's equations predicted everything about light, interference, diffraction, polarization, propagation. You couldn't just throw that away because of one puzzling experiment. Einstein didn't back down. Over the next few years, he kept refining the idea, kept pointing out problems with the wave theory that light quanta could solve. He argued that if radiation was quantized, momentum had to be quantized too. Light quanta didn't just carry energy, they carried momentum. That prediction, strange as it sounded, would eventually be confirmed in 1923 when Arthur Compton showed that X-rays scattered off electrons exactly the way particles with momentum would scatter. Compton scattering, as it's now called, was the final nail in the coffin for anyone still clinging to the pure wave theory. But in 1905, nobody believed Einstein. Nobody except maybe one or two younger physicists who were willing to entertain the idea that maybe, just maybe, the universe was stranger than anyone had imagined, and even they weren't sure. The evidence was circumstantial, the photoelectric effect was real, but there could be other explanations. Maybe something about the way electrons were bound in metals, something nobody had figured out yet. Maybe the wave theory just needed a patch, the way Planck had patched blackbody radiation. Light quanta felt like overkill. It took more than a decade for the physics community to come around. In 1916, Robert Millikan, an American physicist who would go on to win the Nobel Prize, set out to disprove Einstein's photoelectric equation. He spent years building the most precise apparatus anyone had ever constructed for measuring the photoelectric effect, meticulously testing metals, wavelengths, intensities, and when he published his results, he admitted grudgingly that Einstein's equation was correct. The energy of ejected electrons followed Einstein's prediction exactly, E equals h nu minus the work function. Every measurement, every metal, every wavelength, perfect agreement. Millikan still didn't like the light quanta idea. He wrote that Einstein's hypothesis seemed untenable, that it contradicted too much established physics, but the equation worked. The data was undeniable. By the early 1920s, even the skeptics had to admit that something particle-like was happening with light. And in 1921, the Swedish Academy awarded Einstein the Nobel Prize in Physics, not for relativity, not for E=mc², for his work on the photoelectric effect, for the law they called it, not the theory. They weren't ready to endorse the full light quanta hypothesis, but they couldn't ignore the equation. The Nobel Committee's citation carefully avoided the word quanta. They praised Einstein for his discovery of the law of the photoelectric effect. Safe, non-committal, but everyone knew what it meant. Light was made of particles, or at least it behaved like it was. The wave theory wasn't wrong, but it wasn't the whole story either. Here's the thing that makes Einstein's 1905 paper so staggering. He didn't have new experimental data. The photoelectric effect had been known for almost 20 years. The black-body spectrum had been measured to death. Planck had already introduced the constant. Einstein didn't discover a new phenomenon. He just looked at the existing data and asked a question nobody else was willing to ask. What if light actually is quantized? Not as a trick, not as a mathematical convenience, but as a real physical fact about the universe. What if every time you flip a light switch, you're releasing trillions of tiny particles, each one carrying a fixed amount of energy, each one indivisible, each one localized in space like a bullet? That question, simple as it sounds, demolished the classical worldview. Energy was supposed to be continuous. Waves were supposed to be smooth, spread out, infinite in extent. Particles were lumpy, discrete, localized. You couldn't have it both ways. Either light was a wave or it was particles. Pick one. The universe, Einstein was saying, doesn't let you pick. Light is both, or neither, or something else entirely that doesn't fit into the categories humans invented. And if light doesn't follow the rules, what else doesn't? What about electrons? What about atoms? What about matter itself? Those questions would take another 20 years to answer, and the answers would be even stranger than the questions. But the door opened in 1905. Einstein kicked it open with a 20-page paper that most physicists initially ignored. And once that door was open, once the idea of light quanta was out in the world, there was no closing it. Physics would never be the same. By the time Einstein received his Nobel Prize in 1922, the quantum revolution was already underway. Niels Bohr had used quantized energy levels to explain the structure of the atom. Louis de Broglie had proposed that if light could be particles, maybe particles could be waves. The universe was turning inside out. And at the center of it all was this uncomfortable, undeniable fact. Light, the thing humans had been studying for thousands of years, the thing you see with every time you open your eyes, was not what anyone thought it was. It wasn't just waves. It wasn't just particles. It was something new. Something that didn't have a name yet because the language didn't exist. The photon, as it would eventually be called, was neither wave nor particle but both, a quantum object that refused to behave, that broke every rule, and that in breaking those rules revealed a deeper, stranger, more beautiful layer of reality underneath. Einstein's light quanta didn't just solve the photoelectric effect, they shattered the paradigm. And once you shatter a paradigm, once you show that the foundation everyone was standing on is cracked, you can't unshatter it. You can't go back to the old certainties. You have to build something new. And that's exactly what physics spent the next 3 decades doing. Einstein's light quanta solved the photoelectric effect. They explained black body radiation. They gave physicists a tool that worked, that made predictions you could test in a lab. But they created a much bigger problem. If light is made of particles, what about all the experiments that proved light is a wave? Young's double slit, Frenzel's diffraction patterns, the interference fringes that only waves produce. Maxwell's equations, which describe light as oscillating electric and magnetic fields, all of that was still true, still verified, still sitting in textbooks and journals, backed by a century of measurements. You couldn't just erase it because Einstein had a clever idea about energy packets. So here's where physics found itself in the early 1900s. Two contradictory models of light, both correct, both verified by experiment, both essential for explaining different phenomena. Light is a wave when you shine it through two slits. Light is a particle when you shine it on a metal surface. Same light, same universe. Two completely incompatible descriptions. Pick the wrong model for the experiment you're analyzing, and you get nonsense. Pick the right one, and everything works perfectly. But there's no rule for which one to pick except try both and see which one doesn't explode. That tension sat there for years. Physicists used whichever model fit the problem they were working on and tried not to think too hard about the contradiction. Waves on Mondays, particles on Tuesdays. Compartmentalize, calculate, publish, move on. It wasn't satisfying, but it was functional. And for a while, functional was enough. Then in 1923, an American physicist named Arthur Compton performed an experiment that made the particle model undeniable. Compton was studying X-rays, high-energy light with wavelengths shorter than ultraviolet. He fired X-rays at a block of graphite and measured what bounced back. The wave theory made a clear prediction. The scattered X-rays should have the same wavelength as the incoming X-rays, just redirected at different angles. That's what waves do when they scatter. They don't change frequency, they just change direction. The scattered X-rays had longer wavelengths, not slightly longer, noticeably longer. The shift depended on the angle. X-rays bouncing straight back had longer wavelengths than X-rays deflecting at smaller angles. The wave theory couldn't explain that, but the particle theory could. If you treated the X-rays as particles with energy and momentum, and you treated the electrons in the graphite as particles you could collide with, the whole thing became a straightforward collision problem. Billiard balls on a quantum pool table. One photon smacks into one electron. The photon transfers some of its energy and momentum to the electron. The photon keeps going, but with less energy. Less energy means lower frequency, which means longer wavelength. The math was clean. Compton worked out the formula, predicted exactly how much the wavelengths should shift at each angle, and the predictions matched the measurements perfectly. Compton scattering, as it's now called, was the final proof that light carries momentum, not just energy, momentum, real, measurable, particle-like momentum. You couldn't wave that away with clever arguments about wave packets or localized disturbances. Photons, whatever they were, acted like particles in collisions. They transferred momentum the way a moving marble transfers momentum when it hits another marble. Einstein had been right. Light quanta were real, but the wave experiments were also real. Interference patterns don't lie. You can't fake the bands of light and dark that appear when you send light through two slits. Those patterns are the signature of waves overlapping, reinforcing, cancelling. And here's the thing that makes it truly impossible to reconcile. You can run the double-slit experiment with light so dim that only one photon passes through the apparatus at a time. One photon. A single discrete packet of energy, localized at a point, behaving like a particle. Send it toward the two slits and let it hit a detector screen on the other side. Where does it land? If photons are particles, each one should go through one slit or the other, not both. You can't split a particle in half and send the halves through different slits. So you'd expect each photon to make a single dot on the screen, somewhere behind one of the two slits. Run the experiment 1,000 times, send 1,000 photons one at a time, and you should see two clusters of dots on the screen. One cluster behind the left slit, one behind the right slit. That's what particles do. That's not what happens. Send photons one at a time and they land in random places on the screen. But as you accumulate thousands of impacts, tens of thousands, the pattern that builds up is not two clusters, it's an interference pattern, alternating bright and dark bands, stretching across the screen. The same pattern you'd get if you sent a continuous wave through the slits. Each individual photon, traveling alone through the apparatus with no other photons anywhere nearby, somehow interferes with something, and the only thing it can interfere with is itself. Run that result through your brain a few times. A single photon goes through the double-slit apparatus and produces a result that only makes sense if the photon went through both slits simultaneously, not one slit or the other, both, at the same time. The photon exists in a state where it is traveling through both paths, and those two paths interfere with each other before the photon lands on the screen. And then, when it hits the detector, it makes one dot, one impact. Localized, discrete, particle-like. The interference happens before the detection. The particle behavior happens during the detection. Same photon, same event. That is wave-particle duality. Not a metaphor, not a useful approximation, a description of what actually happens when you run the experiment. Light, and as it turns out, every other quantum object in the universe, does not fit into the categories of wave or particle. It does something else, something that doesn't have a good analogy in everyday experience because nothing in everyday experience behaves this way. Throw a baseball at two doorways and it goes through one or the other. It doesn't go through both. Send a water wave toward two gaps and it goes through both. But water waves are made of trillions of molecules acting collectively. A photon is one thing, indivisible, and it goes through both slits. Physicists tried for years to make sense of this. Maybe the photon is a wave that collapses into a particle when you measure it. Maybe it's a particle guided by a wave. Maybe it's neither, and we just don't have the right words. Every explanation sounded either vague or insane. And then, in 1924, a French physicist named Louis de Broglie made the situation worse by proposing that if light can be particles, maybe particles can be waves. De Broglie was a graduate student at the time, working on his doctoral thesis at the University of Paris. He'd been thinking about Einstein's photons and wondering if there was a symmetry. Photons have energy and momentum. Einstein had shown that the energy of a photon equals Planck's constant times its frequency. From relativity, you can derive that the momentum of a photon equals Planck's constant divided by its wavelength. Those equations connect particle properties, energy and momentum, to wave properties, frequency and wavelength. De Broglie asked a simple question. If particles of light have wave properties, do waves of matter have particle properties? He proposed that every particle, electrons, protons, atoms, baseballs, everything, has an associated wavelength. The wavelength equals Planck's constant divided by the momentum. For massive objects moving at everyday speeds, the wavelength is absurdly tiny. A baseball flying at 40 meters per second has a de Broglie wavelength of about 10 to the negative 34 meters. That's a trillion times smaller than an atom. You'd never notice it. But for tiny particles like electrons moving at reasonable speeds, the wavelength is large enough to measure. De Broglie calculated that an electron with typical energy should have a wavelength comparable to the spacing between atoms in a crystal. His thesis advisor didn't know what to make of the idea. It was too strange, too speculative. The advisor sent a copy to Einstein asking for his opinion. Einstein loved it. He saw immediately that de Broglie's hypothesis extended the wave-particle duality to everything, not just light. All of nature, matter and energy, waves and particles, unified under one bizarre framework. With Einstein's endorsement, de Broglie got his PhD. And 3 years later, two American physicists, Clinton Davison and Lester Germer, accidentally proved he was right. Davison and Germer were studying how electrons scatter off metal surfaces. They were firing a beam of electrons at a nickel crystal and measuring where the electrons bounced. It was supposed to be a straightforward materials science experiment. Then their vacuum tube cracked. Air leaked in. The nickel oxidized. They had to heat the crystal to remove the oxide layer, and when they did, the crystal's internal structure changed. The atoms rearranged into larger, more uniform regions. When they resumed the experiment, the scattered electrons did something unexpected. Instead of bouncing off in all directions, they formed a pattern, specific angles where lots of electrons scattered, other angles where almost none did. A diffraction pattern, the kind of pattern you only get from waves. Davison and Germer measured the angles and worked backward to calculate the wavelength. It matched de Broglie's prediction exactly. Electrons, particles with mass and charge and momentum, were behaving like waves. They were diffracting off the rows of atoms in the crystal, the way light diffracts off the slits in Young's experiment. An electron, traveling through space, spreads out like a wave. It doesn't have a single definite position. It has a range of possible positions, a probability distribution, and that distribution interferes with itself when it encounters obstacles. The discovery earned Davison a share of the Nobel Prize in 1937. De Broglie had already won his in 1929. The wave-particle duality wasn't limited to light anymore. It was universal. Everything is both. Everything is neither. The universe at its smallest scales is built from objects that refuse to behave the way objects are supposed to behave. That left physics with a philosophical crisis. If particles are also waves, and waves are also particles, what are they really? What is an electron actually made of? What does it look like when nobody's watching? And what does it mean to watch? Because here's the thing that makes it even stranger. The duality depends on how you measure. Run a double-slit experiment and put detectors at the slits to see which slit each photon goes through. The moment you do that, the interference pattern vanishes. You get two clusters of dots. Particle behavior. Turn the detectors off. Stop measuring which slit the photon goes through, and the interference pattern comes back. Wave behavior. The act of measuring changes the result, not because you're disturbing the photon with clumsy equipment. You can make the measurement as gentle as you want. The change happens because the universe itself behaves differently when you ask different questions. Niels Bohr tried to make sense of this with what became known as the Copenhagen interpretation. Bohr was a Danish physicist, founder of the Institute for Theoretical Physics in Copenhagen and one of the key architects of quantum mechanics. He argued that particles don't have definite properties until you measure them. Before measurement, a photon doesn't have a specific position or a specific momentum or a definite path. It exists in a superposition, a kind of blurred state where all possible outcomes coexist simultaneously. The photon is going through the left slit and the right slit. It's here and there. It's everywhere its wave function says it could be. And then you measure it, you detect it, you interact with it in a way that forces it to give you a specific answer. And at that moment, the wave function collapses. The superposition vanishes. The photon becomes localized. It picks one outcome out of the many possibilities and commits to it. The interference pattern exists because the photon's wave function goes through both slits and interferes with itself. The dot on the screen exists because the wave function collapses into a single position when the photon hits the detector. This is not a comfortable picture of reality. It says the universe at a fundamental level is not deterministic. You cannot predict exactly where a photon will land on the screen. You can only calculate the probability that it will land in a particular region. And it's not that you're missing information. It's not that there's some hidden variable you haven't measured yet that would tell you the exact answer. The universe itself doesn't know the answer until the measurement happens. Before the measurement, the photon doesn't have a position. After the measurement, it does. The act of measurement doesn't reveal a pre-existing fact. It creates the fact. Albert Einstein hated this. He and Bohr argued about it for years. Einstein believed the universe was deterministic, that particles had real properties whether you measured them or not, that probability was just a placeholder for ignorance. He thought quantum mechanics was incomplete, that there was a deeper theory underneath that would restore order and reason. He captured his objection in a letter to Max Born in 1926 with one of the most famous quotes in physics. He wrote, "Quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal but hardly brings us closer to the secret of the old one. I am, at all events, convinced that he does not play dice." Bohr disagreed. He argued that quantum mechanics was complete, that the probabilities were fundamental, that the universe really does play dice. The two men respected each other enormously. They remained friends, but they never resolved the disagreement. Einstein kept searching for a way to prove quantum mechanics wrong or incomplete. Bohr kept defending the Copenhagen interpretation, and the experiments kept siding with Bohr. Every test, every refinement, every attempt to catch quantum mechanics making a mistake came back confirming that yes, this is how the universe works. Particles are waves. Waves are particles. Measurement matters. Probability is real. The double-slit experiment, simple as it sounds, contains the entire mystery. Richard Feynman, one of the greatest physicists of the 20th century, said it outright. In his lectures, he told students that the double-slit experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery. Everything else, all the weirdness, all the counterintuitive results, follows from what happens in that one experiment. A particle goes through two slits and interferes with itself. That single fact is enough to break classical physics. You can't explain it with particles. You can't explain it with waves. You need something new. What's even stranger is that you can extend the experiment, run it with electrons instead of photons. Same result. Interference pattern. Run it with neutrons. Same result. Run it with whole atoms. Same result. In 2003, physicists in Vienna ran a double-slit experiment with molecules, not atoms, molecules. Complex structures made of 60 carbon atoms arranged in a spherical shell, buckyballs they're called. These are objects you can almost see under a microscope, and they still produce an interference pattern. Each molecule, traveling alone through the apparatus, goes through both slits simultaneously and interferes with itself. Wave-particle duality isn't just for light, it's for everything. Matter, energy, all of it. The distinction we draw between particles and waves is a human invention. The universe doesn't care about our categories. De Broglie's hypothesis extended the duality to matter, and experiments confirmed it. But the real legacy of wave-particle duality isn't the experiments. It's the shift in how physicists think about reality. Before quantum mechanics, the goal of physics was to describe what things are. An electron is a particle. Light is a wave. The job was to figure out the properties, measure them, write down the equations. After quantum mechanics, the goal shifted to describing what things do. An electron does particle-like things under some conditions and wave-like things under others. The question of what it is became secondary, maybe even meaningless. Bohr argued that we can't talk about the properties of quantum objects independent of how we measure them. The object and the measurement apparatus form a single system. You can't separate them. Asking what an electron is when nobody's looking is like asking what a tree sounds like when it falls in the forest with no one around. The question assumes a framework that doesn't apply. That philosophical shift disturbed a lot of people. It still does. Physics was supposed to uncover objective truths about the universe, facts that exist whether humans are there to observe them or not. Quantum mechanics says that at some level, observation is part of the reality. You can't factor it out. The observer and the observed are entangled. And that means the universe is fundamentally stranger than anyone wanted it to be. Einstein spent the last decades of his life trying to find a way around this. He proposed thought experiments designed to show contradictions in quantum mechanics. The most famous is the Einstein-Podolsky-Rosen paradox, published in 1935. The paper argued that if quantum mechanics was complete, it would allow for spooky action at a distance, instantaneous connections between particles separated by arbitrary distances. Einstein thought that was absurd. It had to mean quantum mechanics was missing something. Decades later, physicists tested the prediction. Spooky action at a distance is real. Particles can be entangled such that measuring one instantly affects the other, no matter how far apart they are. Einstein was wrong. The universe is that strange. Wave-particle duality is the crack in classical reality that opened the door to everything else quantum mechanics revealed. Superposition, entanglement, uncertainty, tunneling. All of it traces back to the fact that quantum objects don't have definite properties until you measure them. They exist in a state of possibility, spread out over space, over time, over every variable you might want to measure. And then you look, you measure, you ask a question, and the universe gives you an answer picked from the range of possibilities according to rules that are probabilistic at their core. You can't predict the exact outcome. You can only predict the odds. This is not how we experience the world. Chairs don't exist in two places at once. Baseballs don't go through both doorways. You don't see interference patterns when you walk through a hallway. The reason is scale. The quantum effects are real, but for large objects made of trillions of atoms, the interference patterns wash out. The probabilities average. The superpositions collapse so quickly and so thoroughly that the classical behavior emerges. But at the level of individual photons, individual electrons, individual atoms, the quantum nature is undeniable. And the quantum nature says that the universe is not made of things with definite properties. It's made of wave functions, probability distributions, fields of possibility. That's where the story goes next, because once you accept that particles are also waves, you have to ask what the wave actually is. It's not a wave in a medium like sound in air or ripples in water. The luminiferous aether is long dead. The wave isn't in space. The wave is something more abstract, a mathematical object that describes the probability of finding a particle at a given location. And if you take that idea seriously, if you follow the math where it leads, you end up with quantum field theory, a framework where particles aren't objects at all. They're excitations in underlying fields that fill the universe. The photon isn't a thing, it's a ripple in the electromagnetic field. And the electromagnetic field is everywhere, always, waiting for something to disturb it. Wave-particle duality was the impossible truth that forced physicists to accept that reality is weirder than anyone imagined. But it was only the beginning. By the 1920s, physics had a problem that wouldn't go away. Light was a wave. A century of experiments said so. Interference patterns, diffraction, polarization, Maxwell's equations, all of it pointed to waves. And light was also particles. The photoelectric effect, Compton scattering, blackbody radiation, all of that pointed to discrete packets of energy, localized, quantized, behaving like bullets. Both descriptions were correct. Both were experimentally verified, and both were completely incompatible with each other. You couldn't have it both ways, except the universe didn't care what you could or couldn't have. It did both, simultaneously, without apology. The term for this mess was wave-particle duality, and it was driving physicists to distraction. Not because the experiments were unclear. The experiments were pristine. The data was bulletproof. The problem was that nobody could explain what was actually happening. What is light made of? Not how does it behave under these conditions versus those conditions. What is it? Strip away the measurements, the apparatus, the mathematical formalism, and tell me what the thing is that's traveling from the sun to your face right now. And for 2 decades, the best answer physics could give was, it depends on how you look at it. That wasn't good enough. Science is supposed to describe reality, not offer a menu of mutually exclusive options depending on your mood. If light is a wave, it's a wave. If it's a particle, it's a particle. It can't be both. And yet it was. The contradiction sat there unresolved, mocking everyone who tried to make sense of it. And then in the mid-1920s, a new framework started to emerge. Not from one person, not from one breakthrough, but from a collective realization that the whole question was being asked wrong. Light wasn't a wave or a particle, it was something else. Something that didn't exist in classical physics because classical physics didn't have the language for it. Light was a quantum, a discrete excitation of an underlying field, and that field, the electromagnetic field, was everywhere. Always, filling every cubic centimeter of space in the universe. The photon, as it would come to be called, wasn't a thing traveling through space, it was a ripple in the field. A localized disturbance carrying energy and momentum from one place to another. And when you understood that, when you stopped trying to cram quantum objects into classical categories, the contradictions dissolved. Not because they went away, but because you realized you'd been asking the wrong question. The word photon didn't appear until 1926. It was coined by an American chemist named Gilbert Lewis in a paper published in Nature. Lewis was trying to develop a new theory of light and matter, and he needed a term for the particle of light. He borrowed from Greek, phos, meaning light, photon, the particle of light. The name stuck, even though Lewis's theory didn't. Within a few years, everyone was using the word photon, clean, simple, unambiguous. It sounded like a real thing, a particle with a name. And in a way, that helped. It gave physicists something concrete to talk about, a noun they could attach equations to, a mental image they could work with. But the name was almost 20 years late. Einstein had introduced the concept of light quanta back in 1905. For 2 decades, physicists had been calling them light quanta, or energy quanta, or just quanta. The idea existed, it just didn't have a label. Here's what the photon is, stripped down to its core. It is the quantum of the electromagnetic field. That sentence contains the entire answer, but you have to unpack it carefully because every word matters. Start with field. A field, in physics, is a quantity that has a value at every point in space. Temperature is a field. You can measure the temperature at every location in a room and map it. The gravitational field tells you the strength and direction of gravity at every point near a massive object. The electromagnetic field tells you the strength and direction of electric and magnetic forces at every point in space. Fields are not objects. They're not made of stuff. They're properties of space itself, and the electromagnetic field is always there, even in a pitch-black room with no light sources, no charges, nothing. The electromagnetic field exists. It's just in its lowest energy state, the vacuum state, quiet, undisturbed. Now add quantum. In classical physics, fields are smooth. You can add energy to a field continuously. Crank up the temperature a little, a lot, any amount you want. In quantum physics, that's not how it works. Fields are quantized. You can't add arbitrary amounts of energy. You can only add discrete chunks, quanta. The smallest possible disturbance you can create in the electromagnetic field is 1 photon. Add more energy and you get more photons. 2, 3, a billion. But you can't have half a photon. You can't have 1.3 photons. The photon is indivisible. It's the smallest unit of electromagnetic energy that can exist on its own. Think of the field like the surface of a trampoline. The trampoline is always there, stretched flat. That's the vacuum state. Now drop a marble on it. The marble creates a localized dip, a disturbance in the surface. That dip is a photon. Drop another marble and you get another dip. 2 photons. The marbles themselves aren't the field, they're excitations of the field. Ripples. The field is the trampoline, the photon is the ripple, and just like a ripple on water, a photon can move. It propagates through the field, carrying energy from one place to another. When it reaches its destination, when it gets absorbed by an atom or a detector, the energy transfers and the photon ceases to exist. The ripple flattens out. The field returns to its vacuum state at that location. This is a radically different picture from Newton's corpuscles or Einstein's original light quanta. It's not a particle in the sense of a tiny billiard ball flying through empty space. It's a disturbance in something that's everywhere. And that distinction matters because it explains the wave-particle duality. The field is continuous. It exists at every point. A photon, an excitation of that field, inherits some of that continuity. It doesn't have a single well-defined position. It's spread out over a region of space, described by a wave function that tells you the probability of finding the photon at any given location. When you measure the photon, when you detect it, the wave function collapses and the photon shows up at one specific spot. Particle behavior. But before the measurement, the photon is delocalized. Wave behavior. Same object, different aspects of the same underlying reality. The framework that makes this precise is called quantum field theory. It was developed over the course of the 1920s and 30s by physicists, including Paul Dirac, Werner Heisenberg, Wolfgang Pauli, and others. Dirac in particular made a breakthrough in 1927 when he figured out how to quantize the electromagnetic field. He took Maxwell's equations, which describe the classical electromagnetic field, and applied the rules of quantum mechanics. The result was a theory where the electromagnetic field isn't a smooth, continuous entity. It's made of discrete excitations, photons. Each photon has a specific energy, a specific momentum, a specific frequency, and those properties are locked together by simple relationships. The energy of a photon equals Planck's constant times its frequency. The momentum equals Planck's constant divided by its wavelength. Frequency and wavelength are inversely related because the speed of light is constant. High frequency means short wavelength. Low frequency means long wavelength. But the speed is always the same, exactly 299,792,458 meters per second. No exceptions. Why is the speed always the same? Why do photons, and only photons, travel at the cosmic speed limit? The answer is mass, or more precisely, the lack of it. Photons have no rest mass, zero. not approximately zero, not a very small number that's effectively zero, exactly zero. And that changes everything. In special relativity, Einstein's theory of space and time, the speed limit of the universe is not the speed of light. That's a misleading way to phrase it. The speed limit is the speed of causality, the maximum rate at which information or influence can propagate from one place to another. Light happens to travel at that speed, which is why we call it the speed of light. But the deeper reason light travels at that speed is that photons are massless. If a particle has no rest mass, it must travel at the speed of causality. It can't go slower, it can't go faster, it's locked in. The logic comes from Einstein's energy-momentum relation. For any particle, the total energy squared equals the rest mass squared times the speed of light to the fourth power, plus the momentum squared times the speed of light squared. If the particle has mass, it can be at rest. It can have zero momentum and still have energy, the rest energy, mass times the speed of light squared. If the particle has no mass, the rest energy term vanishes. The total energy comes entirely from momentum. And for a massless particle, that forces the speed to be exactly the speed of light, always. A photon doesn't accelerate from zero to light speed. It doesn't have a zero. It's created already moving at light speed, and it continues at light speed until something absorbs it. This has strange consequences. One of them is that from the photon's perspective, if a photon could be said to have a perspective, no time passes during its journey. Special relativity tells you that time dilation depends on speed. The faster you move, the slower your clock ticks relative to someone who's stationary. At light speed, time dilation becomes infinite. Time stops. A photon emitted from a distant star 10 billion light-years away and a photon that just bounced off your hand experience the same subjective duration. None. For the photon, emission and absorption are the same event. The journey you measure in billions of years is to the photon instantaneous. It exists outside of time. Another consequence is that photons don't experience space in the direction they're traveling. Length contraction is the partner to time dilation. As you accelerate toward light speed, distances along your direction of motion shrink. At light speed, they shrink to zero. A photon traveling across the universe doesn't traverse any distance from its own reference frame. The galaxy it left and the detector it's heading toward are in the same place. The entire observable universe, from the photon's point of view, is a single point. These aren't just mathematical curiosities, they're fundamental features of what it means to be massless. And they explain why photons are so different from particles like electrons or quarks, which do have mass. Electrons can be at rest. You can hold one in a trap. You can slow it down, speed it up, change its direction. Photons can't be at rest. They don't have a rest state. They exist only in motion. And the moment you try to stop one, the moment it interacts with something and transfers its energy, it ceases to exist. The photon is gone, absorbed, converted into some other form of energy. The relationship between a photon's energy, frequency, and wavelength is locked by the same equations that caused so much trouble in the early 20th century. Energy equals Planck's constant times frequency. That's the equation Einstein used to explain the photoelectric effect. Frequency is the number of oscillations per second. For visible light, frequencies range from about 400 trillion oscillations per second for red light to 750 trillion for violet. Planck's constant is tiny, about 6.626 times 10 to the negative 34th joule seconds. Multiply that by the frequency and you get the energy of a single photon. For red light, that's about 3 times 10 to the negative 90th joules. For violet, it's about 5 times 10 to the negative 19th. Those are unimaginably small numbers. 100 billion photons of red light carry about as much energy as a mosquito flapping its wings once, but each individual photon carries a precise quantized amount. Wavelength is related to frequency by the speed of light. The speed equals the wavelength times the frequency. Longer wavelength means lower frequency. Shorter wavelength means higher frequency. Red light has a wavelength of about 700 nanometers. Violet is around 400. Infrared, the kind your skin feels as heat, has longer wavelengths, micrometers to millimeters. Ultraviolet has shorter ones, a few hundred nanometers down to about 10. X-rays are even shorter, down to picometers. Gamma rays go shorter still, into the realm of atomic nuclei. All of them are photons. All of them are excitations of the same electromagnetic field. The only difference is the energy and the frequency. Same particle, different energies. Photons are created when something with electric charge accelerates. That's the fundamental rule. An electron sitting still doesn't emit photons. An electron jiggling back and forth does. The acceleration of the charge disturbs the electromagnetic field, and that disturbance propagates outward as a photon. In an antenna, you drive electrons up and down a metal rod at a specific frequency. That creates radio wave photons. In a hot filament, thermal motion jiggles the atoms, and the vibrations produce infrared and visible light photons. In the Sun, nuclear fusion in the core creates high-energy gamma-ray photons, which bounce around inside the Sun for thousands of years, gradually losing energy and converting into visible light photons by the time they reach the surface. Every source of light, every lamp, every star, every glowing object is just charges accelerating in various ways and kicking photons into the electromagnetic field. Atoms emit photons when electrons jump from higher energy levels to lower ones. This is one of the cleanest ways to understand photon emission. Picture an atom. The nucleus sits at the center, protons and neutrons clustered together. Electrons orbit the nucleus, but not in the classical sense. They don't follow well-defined paths like planets around a sun. They occupy orbitals, regions of space where the probability of finding the electron is high. These orbitals have discrete energies. An electron in the ground state, the lowest energy orbital, is stable. It sits there indefinitely unless something disturbs it. If you add energy, you can kick the electron up to a higher orbital. The atom is now in an excited state. It's not stable. The electron wants to drop back down to the lower energy level, and when it does, the energy difference has to go somewhere. It gets emitted as a photon. One photon, with an energy exactly equal to the difference between the two levels. This is why atoms emit light at specific frequencies. Hydrogen, the simplest atom, has a specific set of energy levels. When an electron drops from the second level to the first, it emits a photon with a wavelength of about 122 nanometers. That's ultraviolet. Drop from the third to the second and you get red light, 656 nanometers. Drop from the fourth to the second and you get blue-green, 486 nanometers. Every transition produces a photon with a characteristic wavelength. And because every element has a different arrangement of energy levels, every element has its own unique spectrum. Sodium emits yellow, neon emits red-orange, helium emits a mixture that looks pinkish. You can identify an element just by looking at the light it emits. Astronomers use this to figure out what stars are made of. They split the starlight into a spectrum, look for the characteristic lines, and read off the composition. Hydrogen, helium, carbon, iron, whatever. The photons carry that information encoded in their frequencies. Absorption works the same way in reverse. Shine white light through a gas, and the atoms will absorb photons at specific frequencies. the ones that match the energy differences between their levels. The photon gets absorbed, the electron jumps up, the atom enters an excited state. Later, the electron drops back down and emits a photon, but it can emit in any direction. The light you started with, traveling in one direction, gets scattered. If you look at the transmitted light, you'll see dark lines in the spectrum at those specific frequencies, absorption lines. Stars have absorption lines in their spectra because the outer layers of the star are cooler than the core, and the atoms in those cooler layers absorb photons at their characteristic frequencies. The sunlight you see every day has thousands of absorption lines, called Fraunhofer lines after the scientist who first catalogued them in the early 1800s. They're the fingerprints of the elements in the sun's atmosphere. Photon emission and absorption are not continuous processes, they're quantum jumps. The electron doesn't gradually slide from one energy level to another. It disappears from one orbital and reappears in another instantaneously. During the transition, it's not anywhere in between. It's in a superposition, a quantum state that's a mixture of the two levels, and when the transition completes, the photon appears, fully formed, carrying the exact energy difference. This is what quantization means. Energy doesn't flow smoothly, it jumps in discrete steps, and the photon is the carrier of those steps. This leads to another role the photon plays. It's not just the quantum of light, it's the carrier of the electromagnetic force. In quantum field theory, forces between particles are mediated by the exchange of other particles. The electromagnetic force, the force that makes electrons repel each other and makes protons attract electrons, is mediated by photons. Not the photons you see. These are virtual photons, a term that sounds made up but refers to a real calculational tool in the theory. When two electrons get close to each other, they exchange virtual photons. Those photons carry momentum from one electron to the other, creating the repulsive force. The closer the electrons get, the more photons they exchange, the stronger the force. You don't see the virtual photons. They exist for such a short time that they can't be detected directly. But the effect they produce, the electromagnetic force, is real and measurable. Every time you touch something, every time you feel resistance when you press your hand against a table, that's electrons in your hand exchanging virtual photons with electrons in the table. The force you feel is the sum of trillions of photon exchanges happening faster than you can blink. This picture of forces as particle exchanges is one of the central insights of quantum field theory. It unifies what seemed like separate concepts. Photons are light. They're also the thing that makes charges push and pull on each other. Same particle, same field, two manifestations. Real photons are the ones you detect, the ones you see, the ones that travel across the universe carrying energy. Virtual photons are the ones that mediate forces, the ones that pop in and out of existence during interactions, the ones that never make it to a detector but leave their mark on everything they touch. The distinction is useful but somewhat artificial. Both are excitations of the electromagnetic field. Both follow the same rules. The photon's status as force carrier makes it a member of a larger family. In the standard model of particle physics, the framework that describes all known particles and forces, photons belong to a class called gauge bosons. Bosons are particles with integer spin, a quantum property related to angular momentum. Gauge bosons mediate forces. The photon mediates electromagnetism. The W and Z bosons mediate the weak nuclear force, the one responsible for radioactive decay. Gluons mediate the strong nuclear force, the one that holds quarks together inside protons and neutrons. Gravity, if it fits into the framework at all, would be mediated by a hypothetical particle called the graviton. Though nobody has ever detected one, and there are good reasons to think gravity might work differently. The photon is the best understood of the gauge bosons because electromagnetism is the best understood of the forces. We can calculate photon interactions to absurd precision. Predictions match experiments to better than 1 part in a billion. The agreement is so tight that quantum electrodynamics, the theory of photons and electrons, is sometimes called the most accurate theory in the history of science. Understanding the photon as a field excitation resolves the wave-particle duality, but it also opens new questions. If the electromagnetic field is always there, what happens when you remove all the photons? When you get down to the vacuum state, is the field truly empty? Quantum mechanics says no. Even in the vacuum, the field fluctuates. Virtual photons pop in and out of existence, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. These vacuum fluctuations have measurable effects. They shift the energy levels of atoms slightly, a phenomenon called the Lamb shift, first measured in 1947. They create a tiny force between uncharged metal plates placed close together, the Casimir effect, confirmed experimentally in 1948. The vacuum isn't empty, it's seething with activity, a roiling sea of virtual particles that exist for fractions of a second before vanishing. The photon, real or virtual, is never truly absent. The field is always there, always ready to be excited. The birth of the photon as a concept wasn't a single moment. It was a process spanning decades, from Planck's reluctant quantization in 1900 to Dirac's quantum field theory in the 1920s to the full maturity of quantum electrodynamics in the 1940s. Each step refined the picture, peeled away another layer of confusion, brought the photon into sharper focus. And what emerged was not the particle Newton imagined, not the wave Maxwell described, but something richer. A quantum object that is both and neither, an excitation of a field that fills the universe, a carrier of energy and force, a messenger that connects every charged particle to every other, a ripple in the fabric of space that makes sight possible, that warms your skin, that carries information across the cosmos at the absolute speed limit of reality. The photon is the simplest quantum particle. It has no mass, no charge, no internal structure, and yet it contains within it the entire mystery of the quantum world. Understanding what a photon is means understanding that the universe at its most fundamental level is not made of things, it's made of fields, and particles are what happen when those fields get disturbed. That insight didn't just solve the problem of light, it became the foundation for understanding everything else. By the 1940s, physics had a photon. It had a framework. It had quantum mechanics, a set of rules that described how particles behave at the smallest scales. It had special relativity, a theory that unified space and time. It had Maxwell's equations describing the electromagnetic field. And all of those pieces sat there, half-connected, like a puzzle someone had dumped on the table without bothering to put together. The photon was an excitation of the electromagnetic field. Fine, electrons were quantum particles with wave functions. Great. How did they interact? What happened when a photon hit an electron? How did the electromagnetic force actually work at the quantum level? Classical physics couldn't answer that. Maxwell's equations described fields, not particles. Quantum mechanics described particles, not fields. You needed both. You needed a theory that treated the electromagnetic field as a quantum object, where photons could be created and destroyed, where electrons could absorb and emit them, where the whole dance of light and matter played out according to quantum rules. That theory, when it finally came together, would be called quantum electrodynamics, QED. and it would become the most accurate scientific theory ever constructed. Not approximately accurate, not good enough for most purposes, accurate to better than 1 part in a billion. A theory so precise that if you used it to predict the diameter of North America, you'd be off by less than the width of a human hair. Getting there took 20 years, 3 brilliant physicists working mostly independently, a war that interrupted everything, and a solution so strange that even the people who developed it weren't entirely sure they believed it. The problem started in the 1920s, right after quantum mechanics was formalized. Paul Dirac, a British physicist with a gift for mathematical elegance, wrote down an equation in 1928 that described how electrons behave when you account for both quantum mechanics and special relativity. The Dirac equation, as it's now called, was a masterpiece. It predicted the electron's spin, a quantum property that nobody had put into the theory by hand. It predicted the existence of antimatter, particles with the same mass as electrons but opposite charge, positrons they'd be called, and they were discovered in 1932 exactly as Dirac's equation said they should be. But the equation had a problem. When you tried to use it to calculate what happens when an electron interacts with the electromagnetic field, the math broke. Not in a subtle way. In a catastrophic, everything goes to infinity way. You'd set up the calculation, write down the integrals, start working through them, and the answer would come out infinite. The electron's self-energy, the energy it should have just from interacting with its own electromagnetic field, was infinite. The probability of certain interactions was infinite. The whole framework collapsed into nonsense the moment you tried to do anything practical with it. Physicists knew something was wrong. The infinities were clearly unphysical. Electrons have finite energy. Interactions happen with finite probabilities. The math was trying to tell them something, but nobody could figure out what. For more than a decade, the problem sat there. Dirac himself thought it might mean quantum field theory was fundamentally flawed, that a completely new approach was needed. The war interrupted most theoretical work. Labs switched to military projects. Young physicists got drafted or sent to places like Los Alamos to work on entirely different problems, and the infinities waited. Then in 1947, an experiment changed everything. Willis Lamb and Robert Rutherford, working at Columbia University, measured the energy levels of hydrogen with unprecedented precision. According to Dirac's equation, 2 particular energy levels, the two S1/2 and two P1/2 states, should have exactly the same energy. They didn't. There was a tiny difference. A shift of about 1,000 megahertz, which in energy terms is about 4 millionths of an electron volt. Minuscule, but real, measurable, reproducible. The Lamb shift, as it came to be called, was a crack in the Dirac equation. Something was happening that the theory hadn't accounted for. At almost the same time, another experiment found a different discrepancy. Polycarp Cush, also at Columbia, measured the magnetic moment of the electron. The magnetic moment is a measure of how strongly the electron responds to a magnetic field. Dirac's equation predicted a specific value, a number called the G factor, which should be exactly 2. Cush found it was slightly larger, about 2.0023, a deviation of about 0.1%, tiny but unmistakable. Both experiments pointed to the same conclusion. Quantum electrodynamics, the half-finished theory of how photons and electrons interact, was missing something. The infinities weren't just a mathematical nuisance, they were a signal that the theory was incomplete. And if you could figure out how to handle them, how to extract finite, meaningful predictions from the infinite mess, you'd have a theory that could explain the Lamb shift, the electron's magnetic moment, and everything else about how light and matter interact. 3 physicists solved the problem independently, using 3 completely different approaches. Richard Feynman in the United States, Julian Schwinger, also in the United States, and Shinichiro Tominaga in Japan. They didn't know each other's work at first. Communication across the Pacific was still limited in the late 1940s. Tominaga had been working in isolation during the war, developing his ideas while American bombers were flattening Japanese cities. Feynman and Schwinger were both at American universities, but they approached the problem from opposite directions and barely spoke to each other. And yet, by 1949, all three had arrived at the same place: a working, consistent, predictive theory of quantum electrodynamics. Different methods, same answer. That's usually a good sign you've found something real. Julian Schwinger was the formal one. Born in New York in 1918, he was a child prodigy who published his first physics paper at 16. By his early 20s, he was a professor, known for his mathematical rigor and his ability to work through hideously complicated calculations without making mistakes. Schwinger's approach to QED was to take the existing framework and fix it piece by piece, using every tool in the quantum mechanics and relativity toolkit. He developed a technique called renormalization, a way to systematically subtract the infinities and leave behind finite, physically meaningful results. It wasn't a guess. It was a carefully constructed procedure with rules, with logic, with mathematical elegance. The idea behind renormalization sounds insane at first. You start with a calculation that gives you infinity. You can't use infinity, so you introduce another infinity carefully chosen and subtract it from the first one. If you do it right, the infinities cancel and you're left with a finite number that matches the experiment. It's like balancing your checkbook by adding an infinite amount of debt and an infinite amount of credit and somehow ending up with the correct balance. It works. Nobody really knows why it works, but it does. Schwinger calculated the Lamb shift using renormalization and got an answer that matched Lamb's measurement almost perfectly. He calculated the electron's magnetic moment and got an answer that matched Cauchy's result. He presented his work at a conference in 1947 at the Pocono Manor Inn in Pennsylvania, and the physicists in the room were stunned. The infinities were gone. The theory worked. Schwinger's methods were dense, formal, built on operator algebra and relativistic field theory, but they gave the right answers. Shinichiro Tominaga, working in Tokyo, had come to almost identical conclusions. Born in 1906, Tominaga had studied in Germany in the early 1930s and returned to Japan just as the war was beginning. During the war, he worked on radar technology for the Japanese military, but in his spare time he kept thinking about quantum field theory. He developed a version of renormalization independently, using a slightly different mathematical framework that emphasized the invariance of the theory under changes of reference frame. His papers, written in Japanese and published in Japanese journals during the war, didn't reach the West until after 1945. When they did, physicists realized he'd solved the same problem Schwinger had solved years earlier with no knowledge of what anyone else was doing. Then there was Richard Feynman. Born in 1918 in Queens, New York, Feynman was brilliant, irreverent, and completely uninterested in formalism for its own sake. He'd worked on the Manhattan Project during the war, calculating neutron diffusion for the atomic bomb while simultaneously picking locks, playing bongos, and generally ignoring every rule that wasn't strictly necessary. After the war, he ended up at Cornell, where he started thinking about how to make quantum electrodynamics actually usable. Feynman's approach was the opposite of Schwinger's. He didn't like the operator methods. He didn't like the formalism. He wanted a way to visualize what was happening, to see the interactions, to draw pictures that captured the physics. And so he invented Feynman diagrams. A Feynman diagram is absurdly simple. You draw lines representing particles. straight lines for electrons, wavy lines for photons. You connect them at points called vertices where interactions happen. An electron emits a photon. Two electrons exchange a photon. An electron and a positron annihilate into a photon. Each diagram corresponds to a mathematical expression, an integral you can calculate to get the probability of that interaction happening. The genius of Feynman diagrams is that they make the math visual. You can look at a diagram and immediately understand what's going on. This electron is here, it emits a photon. The photon travels over there, another electron absorbs it. Both electrons change direction. The diagram tells the story. Feynman presented his diagrams at the same Pocono conference where Schwinger gave his formal presentation. The reaction was mixed. Some physicists thought the diagrams were too informal, too much like cartoons. How could you trust a theory based on doodles? But Feynman showed that his diagrams gave the same answers as Schwinger's operator methods, same predictions for the Lamb shift, same predictions for the magnetic moment, same cancellations of infinities. The diagrams weren't just pretty pictures. They were a complete, rigorous calculational tool, and they were vastly easier to use. Within a few years, Feynman diagrams became the standard language of particle physics. You wanted to calculate the probability of an electron scattering off another electron. Draw the diagrams. Electron emits photon, other electron absorbs it, both electrons scatter. That's the simplest diagram, the lowest order contribution. Want more precision? Draw more complicated diagrams. Electron emits photon. Photon briefly turns into an electron-positron pair. Pair annihilates back into a photon. Photon gets absorbed. Each additional diagram adds a correction, a refinement to the prediction. The more diagrams you include, the more accurate your answer gets. The three approaches, Schwinger's, Tomonaga's, and Feynman's, were proven to be equivalent in 1949 by a young physicist named Freeman Dyson. Dyson showed that despite the radically different methods, all three were calculating the same thing. They were all versions of the same underlying theory, quantum electrodynamics. And that theory worked. It predicted the Lamb shift to within experimental error. It predicted the electron's magnetic moment to incredible precision. As experiments got better, QED kept matching them. By the 1960s, the G factor of the electron had been measured to 8 decimal places. QED's prediction matched. By the 1980s, 10 decimal places, still matched. By the 2000s, 12 decimal places. The current experimental value is 2.00231930436153, plus or minus a tiny uncertainty in the last couple of digits. QED predicts 2.002319304361, effectively identical. That level of agreement is unheard of in science. It's like predicting the distance from New York to Los Angeles and being off by the width of a hair. The theory didn't just work for electrons and photons. The framework of QED became the template for understanding all the fundamental forces. The strong nuclear force, the one that holds quarks together inside protons and neutrons, is described by a theory called quantum chromodynamics, QCD, which uses the same mathematical structure as QED. The weak nuclear force, the one responsible for radioactive decay, is described by a theory that's essentially QED with extra particles. The entire standard model of particle physics, the theory that describes every known particle and 3 of the 4 fundamental forces, is built on the foundation QED established. Feynman diagrams are everywhere. Open any particle physics textbook and you'll see them on almost every page. But here's the part that still makes physicists uncomfortable. Virtual particles. Feynman diagrams include them. You draw a wavy line representing a photon connecting two electrons, and that photon is virtual. It's not a photon you can detect. It exists only during the interaction, only as an intermediate step in the calculation. Virtual particles don't obey the normal energy-momentum relationship that real particles do. A real photon has zero mass and travels at the speed of light. A virtual photon can have any effective mass, any speed. It borrows energy from the vacuum, exists for a brief moment allowed by the Heisenberg uncertainty principle, and then vanishes when the interaction completes. This sounds like mathematical fiction, a bookkeeping trick. But virtual particles have real effects. The electromagnetic force between two electrons is mediated by the exchange of virtual photons. You don't see the photons, you see the electrons repelling each other. The force is the result of countless virtual photons being emitted and absorbed, faster than anything could ever measure. The closer the electrons get, the more virtual photons they exchange, the stronger the force. That's how forces work in quantum field theory. Not as mysterious action at a distance, but as the exchange of particles, real or virtual. Virtual particles also cause the vacuum to fluctuate. Even in empty space with no real particles anywhere nearby, the electromagnetic field is seething with activity. Virtual photons pop into existence, exist for fractions of a second, and disappear. Virtual electron-positron pairs do the same. The vacuum isn't empty. It's a roiling sea of quantum fluctuations, and those fluctuations have measurable consequences. The Lamb shift, the tiny energy difference Willis-Lamb measured in hydrogen, is caused by virtual photons. The electron in the atom interacts with the vacuum fluctuations, and that interaction shifts the energy levels slightly. QED calculates the size of the shift by summing over all possible virtual photon exchanges, including the complicated ones where photons turn into particle pairs that annihilate back into photons. The calculation is horrendously difficult. The answer matches the experiment. Another effect of vacuum fluctuations is the Casimir force. Take two uncharged metal plates and place them very close together in a vacuum. Classical physics says nothing should happen. There's no charge, no fields, no reason for the plates to interact. But in QED, the vacuum between the plates and the vacuum outside the plates are different. Outside, virtual photons of all wavelengths can exist. Between the plates, only virtual photons with wavelengths that fit between the plates can exist. Longer wavelengths get excluded. That creates an imbalance. There's more vacuum pressure pushing the plates together from the outside than there is pushing them apart from the inside. The plates attract. The force is tiny, but it's real. It was predicted in 1948 by Dutch physicist Hendrik Casimir and measured experimentally in 1997. The measurement matched the QED prediction. The vacuum has structure. It exerts force. Feynman himself was never entirely comfortable with virtual particles. In his lectures, he emphasized that they were calculational tools, not things you should imagine as little bullets flying back and forth. The diagrams are a shorthand for integrals, a way to organize calculations that would otherwise be impossibly complicated. But whether you think of virtual particles as real or as mathematical conveniences, they work, they give the right answers, and in quantum field theory, that's often the best you can do. The predictive power of QED isn't just about electrons and photons. It extends to any process involving electromagnetism, pair production, where a high-energy photon turns into an electron and a positron, annihilation, where an electron and positron collide and turn into photons, Compton scattering, where a photon bounces off an electron and changes energy, Bremsstrahlung, where an electron decelerates and emits a photon. Every one of those processes can be calculated using Feynman diagrams, and every prediction matches experiment. QED describes how atoms emit light, how lasers work, how particle accelerators create new particles, how X-rays scatter in medical imaging. It's not just a theory about abstract quantum fields, it's a theory that describes the real world with astonishing precision. The success of QED also revealed something unsettling about the nature of reality. At the quantum level, nothing is deterministic. You can't predict exactly what will happen in any given interaction. You can only calculate probabilities. An electron might emit a photon and scatter to the left, or it might scatter to the right. QED gives you the odds, not the outcome. Run the experiment 1,000,000 times and the statistics will match the prediction perfectly, but any single event is fundamentally random. That randomness isn't because you're missing information, it's baked into the theory. The universe at its core plays dice. Einstein hated that. He spent the last decades of his life arguing that quantum mechanics, and by extension QED, had to be incomplete. There must be hidden variables, deeper layers of reality that would restore determinism if only you could access them. He never found them. Experiments kept confirming that quantum mechanics was right and Einstein's intuition was wrong. The universe is probabilistic. QED calculates the probabilities. That's the best anyone can do. By the time Feynman, Schwinger, and Tominaga received the Nobel Prize in 1965, quantum electrodynamics was the gold standard for how to do theoretical physics. It had survived every experimental test. It had predicted phenomena nobody had thought to look for. It had become the foundation for the entire standard model. And it had done all of that with a theory that, when you really think about it, is completely insane. Particles that aren't particles, waves that aren't waves, virtual photons that exist and don't exist at the same time, infinities that you subtract away with other infinities, a vacuum that isn't empty, and yet it works. It works better than any scientific theory ever constructed. Feynman captured the strangeness in a quote that gets repeated in every introductory quantum mechanics class. He said, "I think I can safely say that nobody understands quantum mechanics." He wasn't being modest. He wasn't saying the math is hard or the concepts are subtle. He was saying that at a fundamental level, the theory describes something so far removed from human intuition that true understanding might be impossible. You can learn the rules, you can calculate the predictions, you can verify them in the lab. But grasping what's actually happening, what the universe is actually doing when an electron emits a photon, that might be beyond what human brains are built for. And yet, if you want to understand photons, if you want to know what light really is, QED is the answer. Not a complete answer, because nobody has a complete answer, but the best answer physics has. The photon is an excitation of the electromagnetic field. It's created when a charged particle accelerates. It propagates through space carrying energy and momentum. It can be absorbed by another charged particle. It mediates the electromagnetic force through the exchange of virtual versions of itself. It's governed by probabilities, not certainties, and every detail of that picture, every quirk, every strange prediction has been tested and confirmed to a precision that borders on the absurd. QED isn't just playing with light. It's the rule book for how light plays with everything else. And the universe, it turns out, follows the rules even when they make no sense. Quantum electrodynamics works. The predictions match the experiments, the infinities cancel, the Feynman diagrams give you numbers that match reality to 12 decimal places, and once you have a theory that works that well, once you've nailed down the rules for how photons and electrons interact, you start asking a different kind of question. Not what is a photon, but what do photons do? Where are they? How many are there? What role do they play in the universe at large? The answer to that last question is everywhere and everything. Photons are not just the messengers of sight, not just the particles you detect in a lab or the things that make your phone screen glow. They are the dominant form of information transfer in the universe. Every piece of knowledge we have about anything beyond arm's reach came to us on the back of a photon. The sun, the moon, the planets, the stars, every galaxy ever photographed, every nebula, every black hole accretion disk, every distant quasar sitting at the edge of the observable universe, all of it is known to us because photons made the trip. They left those objects, traveled across space for years or millennia or billions of years, and eventually hit a detector, a telescope mirror, a piece of film, a charged coupled device, and in doing so they told us a story. No other particle does this. Neutrinos zip through the universe, barely interacting with anything, but they're nearly impossible to catch, and they carry almost no directional information. You can't form an image with neutrinos. Cosmic rays, high-energy protons, and atomic nuclei reach Earth from deep space, but they get deflected by magnetic fields along the way. You can't trace them back to their source. Gravitational waves, ripples in space-time itself, carry information about colliding black holes and neutron stars, but the detectors are phenomenally difficult to build and the signals are rare. Photons are easy. Photons are everywhere. Photons are the universe's preferred method of communication. If you want to know what's out there, you look, and looking means catching photons. Start with the most important photons in the universe, the cosmic microwave background, the CMB, fossil light from the Big Bang. Right now, as you sit wherever you are being bathed in photons that have been traveling for more than 13 billion years. They were emitted when the universe was 380,000 years old, a glowing plasma of hydrogen and helium cooling down enough for atoms to form. Before that moment, the universe was opaque. Photons couldn't travel more than a tiny distance before running into an electron and scattering. The whole cosmos was a fog, glowing hot, dense, impenetrable. Then the temperature dropped below about 3000 Kelvin, and suddenly electrons could bind to protons. Neutral hydrogen formed. The fog cleared. Photons that had been trapped, bouncing around in the plasma, were suddenly free to travel. And they've been traveling ever since. The light from that moment, the moment the universe became transparent, is still here. It didn't disappear, it just got stretched. The expansion of the universe stretched the wavelengths of those photons from visible and infrared all the way into the microwave range. What was once a blazing orange glow is now a faint microwave hiss at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. But it's everywhere. Every cubic centimeter of space contains about 400 CMB photons. That's more photons than there are atoms by a long shot. The CMB is the most abundant source of photons in the universe. It's also the most uniform. No matter which direction you look, the temperature of the CMB is the same to about 1 part in 100,000. Tiny fluctuations exist, hot spots and cold spots, and those fluctuations are the seeds that grew into galaxies and clusters and the large-scale structure of the universe. But the overall picture is staggeringly smooth. Arno Penzias and Robert Wilson discovered the CMB by accident in 1965. They were radio astronomers working at Bell Labs in New Jersey, trying to calibrate a large horn antenna for satellite communication work. They kept picking up noise, a persistent static hiss that wouldn't go away no matter what they did. They cleaned the antenna. They checked the electronics. They even removed a pair of pigeons that had been nesting inside and scrubbed out the, let's call it, biological debris the birds had left behind. The noise didn't change. It was coming from every direction all the time with the same intensity. They didn't know what it was. They called it a problem. It wasn't a problem. It was the echo of the Big Bang. Penzias and Wilson had stumbled onto the most important cosmological discovery of the 20th century without realizing it. They published a short paper in the Astrophysical Journal describing the excess antenna temperature they'd detected, playing it safe, not claiming anything too bold. A separate paper by a team of physicists at Princeton, led by Robert Dicke, explained what Penzias and Wilson had actually found. The CMB, the relic radiation from the early universe, the smoking gun that proved the Big Bang had happened. Penzias and Wilson won the Nobel Prize in 1978. The pigeons did not. The CMB has been mapped in exquisite detail since then. The Cosmic Background Explorer (COBE), launched in 1989, produced the first full sky map and confirmed that the spectrum of the CMB is a perfect blackbody, exactly what the Big Bang model predicts. The Wilkinson Microwave Anisotropy Probe (WMAP), launched in 2001, mapped the temperature fluctuations with much higher resolution. And the Planck satellite, launched by the European Space Agency in 2009, pushed the resolution even further. Planck's maps show the CMB in stunning detail, revealing the tiny ripples in temperature that correspond to density fluctuations in the early universe. Those ripples tell you the age of the universe, the rate of expansion, the amounts of ordinary matter and dark energy. The entire cosmological model, the story of how the universe evolved from a hot, dense state to the vast, cold expanse we see today, is written in the pattern of CMB photons hitting your detector. The CMB accounts for roughly 90% of all the photon energy in the universe. Not 90% of the visible light, 90% of all photons, period. Every star, every galaxy, every quasar, all of it combined is a rounding error compared to the flood of microwave photons left over from the Big Bang. The universe is full of light. Most of it is just too cold and too redshifted for your eyes to see. Then there are the stars. Stars are photon factories. Fusion reactions in the core of a star smash hydrogen nuclei together to form helium, and the mass difference gets converted into energy. That energy comes out as photons, high-energy gamma rays at first, produced in the core where the fusion happens. Those gamma rays try to escape, but the star is dense. The photons scatter off electrons, off ions, bouncing around randomly in a process called a random walk. Each time a photon scatters, it loses a bit of energy. Gamma rays become X-rays. X-rays become ultraviolet. Ultraviolet becomes visible light. By the time the photon finally works its way from the core to the surface, it's been scattered trillions of times, and its energy has dropped to the range we call visible light. In the Sun, this process takes about 100,000 years. A photon produced in a fusion reaction at the center of the Sun will take roughly 100 millennia to random walk its way to the surface. Once it breaks free, it travels in a straight line, no more scattering, and reaches Earth in about 8 minutes and 20 seconds. The light you see when you look at the Sun was created 100,000 years ago in the core and spent most of that time bouncing around inside, slowly working its way outward. The sunlight that hit your face this morning started its journey before humans existed. Stars pump out photons at a staggering rate. The Sun emits about 4 times 10 to the power of 45 photons per second. That's a 4 with 45 zeros after it. Every second, most of those photons fly off into space and never hit anything. A tiny fraction, about 1 part in 2 billion, intercepts Earth. That's still an enormous number. About 10 to the power of 34 photons hit the Earth's atmosphere every second. Some get absorbed by the atmosphere, some get scattered, which is why the sky is blue. Some make it to the surface and get absorbed by the ground, by oceans, by plants, by your skin. Solar energy, the energy that drives weather, that powers photosynthesis, that keeps the planet warm enough for liquid water and life, is all photon energy. Every watt of sunlight is a stream of photons delivering energy from the sun's core to Earth's surface. Photosynthesis is one of the most important photon-driven processes in the universe. Plants, algae, and certain bacteria capture photons in the visible range and use the energy to split water molecules and fix carbon dioxide into sugars. The photons get absorbed by molecules called chlorophyll, which are tuned to absorb red and blue light and reflect green, which is why plants look green. The absorbed energy kicks an electron into a higher energy state, and that electron's energy gets funneled into a chain of chemical reactions that ultimately produce glucose and release oxygen. Nearly all the oxygen in Earth's atmosphere, the stuff you're breathing right now, was produced by photosynthesis, by photons hitting chlorophyll and starting a cascade that converts carbon dioxide and water into sugar and oxygen. Life on Earth runs on sunlight, on photons. Humans figured out how to harness photons directly. The first practical application was solar cells, photovoltaic devices that convert light into electricity. The photoelectric effect, the same phenomenon Einstein explained in 1905, is the basis for every solar panel ever built. A photon hits a semiconductor, typically silicon, and if the photon's energy is high enough, it knocks an electron loose. The electron flows through a circuit, creating a current. Direct conversion of light into electricity, no moving parts, no combustion, just photons and electrons. The first solar cell was built in 1954 at Bell Labs, the same place where the CMB would be discovered a decade later. The early cells were inefficient, converting less than 6% of sunlight into electricity. Modern silicon solar cells are around 20 to 22% efficient. Perovskite silicon hybrid cells have pushed that to about 30% in lab settings. There's a theoretical maximum, the Shockley-Queisser limit, which says that a single-junction solar cell can't do better than about 33% because of the way photon energy gets wasted as heat. But even at 30%, solar panels work. They're everywhere now. Rooftops, deserts, satellites, the International Space Station. Every photon that hits a solar cell and generates an electron is Einstein's photoelectric effect in action, the same quantum process that kicked off the quantum revolution. Lasers are another way humans play with photons. The word laser is an acronym: light amplification by stimulated emission of radiation. The key word is stimulated. Normally, when an atom in an excited state drops to a lower energy level, it emits a photon spontaneously. The photon comes out in a random direction with a random phase, spontaneous emission. Lasers work by stimulated emission. If a photon with exactly the right energy passes by an excited atom, it can trigger the atom to emit a second photon that's identical to the first. Same energy, same direction, same phase. The two photons are coherent. They're copies. If you set up a system where lots of atoms are excited and you bounce photons back and forth between mirrors, you get a cascade. One photon stimulates emission of two photons. 2 become 4, 4 become 8. The light builds up, all of it coherent, all of it traveling in the same direction, all of it in phase. That's a laser beam, coherent light. The first working laser was built in 1960 by Theodore Myman at Hughes Research Laboratories. It used a ruby crystal as the medium and produced pulses of red light. The announcement was met with skepticism. Some called it a solution looking for a problem. Within a decade, lasers were everywhere. CD players, barcode scanners, laser pointers, fiber optic communication, surgery, cutting and welding, scientific research, LIDAR. The list is endless. Lasers are now so common that you probably interact with several every day without noticing. Every time you scan a product at a grocery store, a laser is reading a barcode by bouncing photons off the black and white stripes. Every time you play a Blu-ray, a blue laser is reading microscopic pits on a spinning disc. Every time you send data over the internet, there's a good chance that data is being transmitted as pulses of laser light through an optical fiber. Optical fibers are thin strands of glass, thinner than a human hair, designed to guide light over long distances with minimal loss. Light enters one end of the fiber and bounces along the inside, reflecting off the walls, until it exits at the other end. The fiber is so pure that light can travel hundreds of kilometers before the signal gets too weak to detect. Optical fiber networks carry about 95% of global internet traffic. Every email, every video stream, every website you load, the data is being converted into pulses of light, fired down a fiber, and converted back into electrical signals at the other end. The entire information infrastructure of modern civilization runs on photons. Then there's quantum technology. This is where photons stop being just carriers of energy or information and start becoming tools for doing things that classical physics says are impossible. Quantum computing is the most hyped example. Classical computers process information as bits, ones and zeros, definite states. Quantum computers use qubits, quantum bits, which can exist in superpositions of 0 and 1 simultaneously. A qubit can be both at the same time, at least until you measure it. That lets quantum computers explore many possible solutions to a problem in parallel, which for certain types of calculations gives them a massive advantage over classical computers. Photons make good qubits. They're easy to generate, easy to manipulate, and they don't interact much with their environment, which means they stay in superposition longer than most other quantum systems. A photon's polarization, the direction its electric field oscillates, can encode a qubit. Horizontal polarization is 0. Vertical is 1. Diagonal polarization is a superposition of both. You can create entangled photons, pairs of photons whose quantum states are linked no matter how far apart they get. Measure one and you instantly know something about the other, even if it's on the other side of the galaxy. Entangled photons are the backbone of quantum communication and quantum cryptography. Quantum cryptography uses photons to create encryption keys that are provably secure. The most common protocol is called quantum key distribution, QKD. You send photons in random polarization states to a receiver. The receiver measures them. Because of quantum mechanics, any eavesdropper trying to intercept the photons will disturb their states in a detectable way. You can check for that disturbance and know if someone was listening. If the channel is clean, you use the results to generate a shared key that you can use to encrypt messages. The security doesn't come from complicated math, it comes from the laws of quantum mechanics. Measuring a quantum system changes it. That's not a limitation, it's a feature. The first quantum key was distributed over an optical fiber in 1997 by a team led by Anton Zeilinger in Austria. Since then, the technology has been commercialized. There are quantum communication networks in China, Europe, and the United States. China launched a satellite called Massless in 2016 that demonstrated quantum key distribution between space and ground stations over distances of more than 1,200 kilometers. The satellite generates entangled photon pairs and sends them to ground stations in different cities. The photons stay entangled even after traveling through space, and the ground stations use them to establish secure keys. It's the beginning of what some researchers call the quantum internet, a network where information is transmitted and processed using quantum states rather than classical signals. Photons are also the reason we can observe the universe at all. Astronomy is, at its core, the science of catching photons. Every telescope, from Galileo's first refractor to the James Webb Space Telescope, is just a really good photon collector. The bigger the mirror or lens, the more photons you can gather, the fainter the objects you can see. When you look at an image from the Hubble Space Telescope, you're looking at photons that traveled for billions of years across expanding space, hit Hubble's mirror, got focused onto a detector, and turned into electrical signals that got beamed down to Earth, processed and turned into a picture. Every detail in that picture is information carried by photons. The cosmic microwave background gives you the universe at 380,000 years old. Visible light from distant galaxies gives you the universe as it looked billions of years ago, when those galaxies were young and the stars inside them were just forming. X-rays from black hole accretion disks tell you about matter being torn apart and heated to millions of degrees before it falls past the event horizon. Gamma rays from supernovae tell you about the most violent explosions in the cosmos. Infrared light from dusty star-forming regions tells you where new stars are being born. Every wavelength, every band of the electromagnetic spectrum is a different window into the universe, and every window is opened by photons. There's no other way to do it. You can't send a probe to a distant galaxy. Even if you could, it would take billions of years to get there, traveling at any remotely achievable speed. The galaxy would have evolved beyond recognition by the time your probe arrived. You can't reach out and touch a star. You can't scoop up a sample of intergalactic gas and bring it back to a lab. The only thing that makes the trip, the only thing that crosses those unimaginable distances and reaches you in a time frame shorter than the age of the universe, is light. Photons are the only messengers. The cosmos is silent except for the stories photons tell, and they tell those stories in extraordinary detail. Spectroscopy, the science of splitting light into its component wavelengths and analyzing the pattern, lets you read the chemical composition of an object without ever touching it. Every element has a unique set of spectral lines, the wavelengths at which it absorbs or emits light. When light from a star passes through its outer atmosphere, atoms in that atmosphere absorb photons at specific wavelengths. The result is a spectrum with dark lines, absorption lines, at those wavelengths. Match the lines to known elements, and you've identified what the star is made of. Hydrogen, helium, carbon, iron, whatever. This technique, invented in the 1800s, is how astronomers discovered that the sun and the stars are made of the same stuff as Earth. Before that, people assumed stars might be made of some exotic substance unique to the heavens. Spectroscopy proved they're just hot balls of gas, mostly hydrogen and helium, with traces of heavier elements. Nothing exotic, just chemistry and physics. You can go further. The Doppler shift, the change in wavelength when a source is moving relative to you, lets you measure the speed of distant objects. If a galaxy is moving away from you, its light gets stretched to longer wavelengths, redshifted. Moving toward you, the light gets compressed to shorter wavelengths, blue-shifted. Edwin Hubble used this in the 1920s to show that distant galaxies are receding from us, and the farther away they are, the faster they're moving. That observation, made by analyzing the spectra of photons that had traveled for millions of years, is the evidence for the expanding universe. The discovery that changed cosmology forever came from photons and their wavelengths. Photons also carry information about the gravitational fields they passed through. Light bends when it travels near a massive object, not because gravity pulls on photons directly, but because gravity curves space-time and photons follow the curved paths. This is gravitational lensing. A massive galaxy cluster sitting between you and a more distant galaxy will bend the light from that distant galaxy, distorting its image, sometimes splitting it into multiple images or stretching it into arcs. Astronomers use gravitational lensing to map the distribution of dark matter, which doesn't emit light but does curve space-time. The photons act as probes, revealing the invisible mass by how they bend. All of this, every application, every observation, every piece of technology that uses light, depends on the fact that photons behave in predictable ways. They have energy proportional to their frequency. They carry momentum. They interact with charged particles. They can be absorbed, emitted, scattered, reflected, refracted. They travel at the speed of light. They don't experience time. They're massless. They're quantum objects that exist in superpositions and can be entangled. Those properties, strange as they are also reliable, consistent, testable. You can build entire industries on the back of those properties because the universe doesn't change the rules. And yet, for all that we've learned, for all the ways we've harnessed photons, there are still things we don't understand. The vacuum fluctuations, the virtual particles popping in and out of existence, where does that energy come from? Why does the vacuum have structure? Why is the cosmological constant, the energy density of empty space, so small compared to what quantum field theory predicts? QED says the vacuum should have an energy density about 120 orders of magnitude larger than what we observe. That's not a small discrepancy. That's the worst prediction in the history of physics, and nobody knows why the universe doesn't match the theory. Photons are also connected to some of the deepest unsolved problems in physics. Dark energy, the thing that's causing the expansion of the universe to accelerate, doesn't interact with photons at all. It doesn't emit light. It doesn't absorb light. It doesn't scatter light. It's invisible to every photon-based observation we can make. We only know it's there because of its gravitational effects, because the universe is expanding faster than it should if ordinary matter and dark matter were the only things around. But we can't see it. Photons, the ultimate messengers, can't tell us what dark energy is. And then there's the question of why photons exist at all. Why is the universe built this way? Why do massless particles carry the electromagnetic force? Why is light quantized? Why does quantum field theory work? Those aren't questions QED can answer. QED takes the photon as a given, a fundamental excitation of the electromagnetic field, and builds everything else from there. But it doesn't explain why the electromagnetic field exists, or why it has the properties it does, or why the universe chose this particular set of rules and not some other set. Those questions sit at the edge of what we know. The photon, for all its familiarity, for all the ways we've studied it and used it and bent it to our purposes, is still wrapped in mystery. We know what it does. We can calculate its behavior to 12 decimal places. We can build technologies that wouldn't work if we didn't understand it. But ask what it really is. Ask why the universe works this way, and the answers get slippery. The photon is the most studied object in physics. It's also, in some ways, the least understood. Quantum electrodynamics works. It predicts the electron's magnetic moment to 12 decimal places. It explains every photon interaction ever measured. It gave us lasers, solar panels, fiber optics, quantum cryptography, and a framework for understanding 3 of the 4 fundamental forces. QED is the most successful scientific theory ever constructed. And yet, after a century of studying light, after all the experiments, all the mathematics, all the technological marvels we've built on the back of photon physics, there are questions we still can't answer. Not small questions, not details that need refinement, fundamental questions about what photons are, how they work, and what their existence says about the nature of reality. The biggest mystery sits right at the heart of quantum mechanics: measurement, observation, the act of looking. When you send a photon through a double-slit apparatus, it behaves like a wave. It goes through both slits, interferes with itself, and produces a pattern of bright and dark bands on a screen. That's been verified thousands of times. It's not controversial, but put detectors at the slits to see which one the photon goes through, and the interference pattern vanishes. The photon suddenly behaves like a particle, one dot on the screen behind one slit. Turn the detectors off and the pattern comes back. The presence or absence of measurement changes the outcome, not because the detector physically bumps the photon or adds noise to the system. You can make the measurement as gentle as you want. The change happens because the universe treats measured events differently from unmeasured ones. This is the measurement problem, and it's been sitting there since the 1920s. Nobody has solved it. The Copenhagen interpretation, the standard textbook explanation developed by Niels Bohr and Werner Heisenberg, says that quantum systems exist in superpositions, multiple states at once, until you measure them. Before measurement, the photon doesn't have a definite position or path. It's spread out over all possible positions, all possible paths. The act of measurement collapses the wave function. The photon picks one outcome from the cloud of possibilities and commits to it. After measurement, it has a definite position. Before measurement, it didn't. That sounds like an answer until you ask what measurement actually is. What counts as an observation? Does it require a conscious observer, a human looking at the result? Or does any interaction with a macroscopic object count? If a photon hits a detector, and the detector registers it, but nobody looks at the readout, has the wave function collapsed? What if the detector is connected to a computer that stores the result, but the computer isn't turned on? What if the computer is on, but nobody ever checks the file? At what point does the photon stop being a wave and become a particle? When does the superposition end and the definite outcome begin? The Copenhagen interpretation doesn't answer that. It says measurement happens when a quantum system interacts with a classical measuring device, but it doesn't define classical. It draws a line between the quantum world and the classical world and says the rules change when you cross it, but it doesn't tell you where the line is. Bohr argued that the question was meaningless, that you can't separate the quantum system from the apparatus you use to measure it. The two form a whole, and trying to dissect what's happening during the measurement is like asking what color sound is. The question doesn't apply. A lot of physicists found that unsatisfying, still do. Eugene Wigner, a Hungarian-American physicist and Nobel laureate, pushed the issue in the 1960s by proposing a thought experiment now called Wigner's friend. Imagine you're outside a lab. Inside the lab, your friend is performing a quantum measurement on a photon. From your friend's perspective, the measurement happens. The wave function collapses. The photon has a definite state. But from your perspective, standing outside, you haven't measured anything yet. From your point of view, the entire lab, including your friend and the photon, is still in a superposition. Your friend is in a state of having measured the photon and a state of not having measured it simultaneously. Only when you open the door and ask your friend what happened does the wave function collapse for you. So who's right? Did the wave function collapse when your friend measured the photon or when you measured your friend's result? Wigner's conclusion was that consciousness must play a role. The wave function collapses when a conscious observer becomes aware of the outcome. That's the only way to make sense of the scenario. But that opens a whole other can of worms. What counts as conscious? Does a dog collapse wave functions? A fly? A bacterium? A thermostat? If consciousness is required, then physics depends on biology, on neuroscience, on defining something, consciousness, that nobody has successfully defined. Most physicists hate this. They don't want consciousness in their equations, but nobody has come up with a better answer. There are alternatives to the Copenhagen interpretation. Many worlds is one of them, proposed by Hugh Everett in 1957. In Everett's version, the wave function never collapses, ever. When you measure a photon and it has two possible outcomes, both outcomes happen. The universe splits. In one branch, you measure the photon going through the left slit. In another branch, you measure it going through the right slit. Both branches are equally real. Both versions of you exist, each in a separate universe, each unaware of the other. The wave function doesn't collapse, it just expands to encompass all possible outcomes simultaneously. Measurement doesn't create reality, it creates branching realities. Many worlds solves the measurement problem by denying that measurement is special. Every quantum event splits the universe. Every time a photon interacts with anything, every time an electron decays, every time any quantum process happens anywhere in the cosmos, the universe branches. You're constantly splitting into countless copies of yourself, each experiencing a slightly different version of reality, and you never notice because each branch is isolated from all the others. It's an elegant solution in some ways. It takes the math of quantum mechanics seriously and doesn't add any new ingredients. No collapse, no special role for observation, no consciousness required. Just the Schrödinger equation running forward in time, forever. But it's also completely untestable. By definition, you can never observe another branch. You can never communicate with your alternate selves. The theory makes the same predictions as the Copenhagen interpretation for every experiment you could ever perform. So why prefer it? Because it feels cleaner? Because it doesn't require a mysterious collapse. That's philosophy, not physics. And most physicists aren't comfortable with a theory that postulates an infinite number of unobservable universes just to avoid answering what happens during measurement. Then there's the pilot wave theory, originally proposed by Louis de Broglie in 1927 and revived by David Bohm in 1952. In this version, particles are always particles. They always have definite positions and definite velocities, but they're guided by a wave, a pilot wave, that fills space and tells the particle where to go. The photon goes through one slit, not both, but the pilot wave goes through both, and the wave interferes with itself, creating a pattern that guides where the photon is likely to end up. Measurement doesn't collapse anything, it just reveals where the particle was all along. Pilot wave theory is deterministic. If you knew the exact position and velocity of every particle in the universe and the shape of all the pilot waves, you could predict the future with perfect accuracy. No randomness, no probabilities. The apparent randomness in quantum mechanics is just ignorance of the initial conditions. Einstein would have loved this. God doesn't play dice. The universe is clockwork all the way down. But pilot wave theory has its own problems. The pilot wave is non-local. It responds instantaneously to changes anywhere in the universe. Disturb a particle here and the wave everywhere adjusts immediately. That violates the spirit of relativity, which says nothing can travel faster than light. Pilot wave theorists argue that information doesn't travel faster than light, just the wave. And you can't use the wave to send signals, so relativity isn't really violated. It's a subtle distinction, and not everyone buys it. Also, the pilot wave is invisible. You can never measure it directly. You can only infer its existence from the behavior of particles. It's one more layer of hidden machinery added to make the theory work. So here we are, three major interpretations of quantum mechanics. Copenhagen says measurement collapses the wave function but doesn't explain what measurement is. Many worlds says the wave function never collapses but postulates infinite unobservable universes. Pilot wave theory says particles are always particles but requires non-local hidden waves guiding them. All three make the same experimental predictions. All three explain the double-slit experiment, the photoelectric effect, every quantum phenomenon ever observed, and none of them can be ruled out by experiment. The question of what actually happens when a photon is measured, what's really going on behind the math, remains open. Not because we lack data, because the data underdetermines the theory. Multiple frameworks fit the facts, and we don't have a way to choose between them. That uncertainty extends to the photon's relationship with spacetime itself. From the photon's perspective, if the concept even applies, time doesn't pass. Special relativity says that as you approach the speed of light, time dilation increases. Your clock ticks slower and slower relative to someone at rest. At exactly the speed of light, time dilation becomes infinite. Time stops. A photon emitted from a star 10 billion light-years away experiences its entire journey as a single instantaneous event. No duration, no time. Emission and absorption happen at the same moment from the photon's point of view. Length contraction does the same thing to space. Distances along the direction of motion shrink as you speed up. At light speed, they shrink to zero. The galaxy the photon left and the detector it's heading toward are, from the photon's perspective, in the same place. The 10 billion light-years of space separating them is compressed to nothing. From outside, from your perspective, the photon has a journey. It travels a measurable distance over a measurable time. From inside, from the photon's frame of reference, there is no journey, there is no distance, there is no time. The entire history of the photon, from birth to death, is a single point in space-time. What does that mean? You can't ignore it as a quirk of the math. Relativity isn't optional. The equations work. The predictions match every experiment ever done. Muons created in the upper atmosphere by cosmic rays reach the ground because of time dilation. They decay too quickly to make the trip at the speed they're traveling, unless time slows down for them, which it does. GPS satellites have to account for both time dilation from their speed and gravitational time dilation from Earth's gravity, or their clocks would drift out of sync and the system would fail. Relativity is as real as gravity, and relativity says photons exist outside of time. But how can something exist outside of time and still participate in events? The photon is emitted. That's an event. It propagates. That's a process. It gets absorbed. That's another event. From your perspective, those events are separated by time. From the photon's perspective, they're simultaneous. The photon is born and dies in the same instant. And yet, during that instant that isn't an instant, the photon carries information. It carries energy. It travels across space. How does something that doesn't experience time do anything? Nobody knows. Relativity describes what happens. It doesn't explain how it's possible for something to be both timeless and dynamic. The photon is the most extreme example of this paradox because it's the only thing that always travels at light speed. Massive particles can approach light speed but never reach it. Photons are always there. They're born at light speed, they live at light speed, they die at light speed. They're the edge cases, the boundary of what relativity allows. And the boundary is strange. This weirdness gets worse when you try to combine relativity with quantum mechanics. General relativity, Einstein's theory of gravity, says space-time is a smooth, continuous fabric that can be curved by mass and energy. Quantum mechanics says everything is quantized, discrete, chunky. Light comes in photons. Energy comes in packets. There's a smallest possible distance, the Planck length, about 10 to the negative 35 meters. and a smallest meaningful time interval, the Planck time, about 10 to the negative 43 seconds. Below those scales, the concepts of distance and time stop making sense. Space-time itself becomes quantum foam, a seething mess of fluctuations where geometry isn't fixed. Photons live in both worlds. They're quantum particles, excitations of a field, governed by the rules of QED, and they move through space-time, which is supposed to be smooth and continuous. When space-time is nearly flat, when gravity is weak, that's fine. QED works perfectly. But near a black hole, where space-time is curved so severely that not even light can escape, what happens? Does the photon still follow the rules of quantum mechanics? Does it still propagate as a wave? Does it still interact with electrons the same way? General relativity says yes, as long as you account for the curved geometry. But quantum mechanics doesn't have a version of itself that works in strongly curved spacetime. QED assumes spacetime is flat, or at least nearly so. It breaks down when gravity gets strong. Physicists have been trying to merge quantum mechanics and general relativity for nearly a century. The goal is a theory of quantum gravity, a framework that describes what happens when quantum effects and gravitational effects are both important. Near the singularity at the center of a black hole, in the first moments after the Big Bang, anywhere spacetime is both quantum and curved, nobody has succeeded. There are candidates. String theory is one, loop quantum gravity is another. Both make progress on certain problems. Neither is complete. Neither makes testable predictions that differentiate it from the alternatives, and both struggle with photons. In string theory, particles aren't points. They're tiny loops of vibrating string. Different vibration patterns correspond to different particles. A photon is one pattern. An electron is another. Gravity, if string theory is right, is carried by another pattern called the graviton. The theory unifies all the forces and particles into a single framework. Elegant. Except it requires extra dimensions, not the 3 of space and 1 of time we experience, 10 dimensions, or 11, depending on which version you use. The extra dimensions are compactified, rolled up so small we never notice them, and the theory makes no firm predictions about anything we can currently measure. It's beautiful math. It might describe reality, but we don't know. Loop quantum gravity takes a different approach. It says space-time itself is quantized. Space isn't continuous. It's made of discrete chunks, loops, woven together into a network. Geometry is emergent from the interactions of these loops. Photons, in this picture, are excitations that propagate through the network. But the details are murky. How does a photon behave when spacetime is chunky? How do you recover the smooth, continuous spacetime of general relativity from a network of loops? The math is hard, progress is slow, and again, no testable predictions yet. The photon sits at the center of these problems because it's both quantum and relativistic. It's the quantum of the electromagnetic field. It's also the thing that moves at the cosmic speed limit, the thing that experiences no time, the thing that defines causality. If you're going to unify quantum mechanics and relativity, you have to get the photon right, and nobody has figured out how. Then there's non-locality. Entanglement. Spooky action at a distance, as Einstein called it, dripping with sarcasm. Create a pair of photons in a specific quantum state, an entangled state, and the two photons are connected. Measure the polarization of one, and you instantly know the polarization of the other, no matter how far apart they are. Not because they're sending signals to each other, there's no signal. The connection is deeper than that. The two photons share a single quantum state. They're not two independent objects. They're two parts of one system, and measuring one part affects the whole. Einstein hated this. He and two colleagues, Boris Podolsky and Nathan Rosen, wrote a paper in 1935 arguing that entanglement proved quantum mechanics was incomplete. If measuring one photon instantly affects another photon a million kilometers away, either information is traveling faster than light, which violates relativity, or the photons had definite properties all along, and quantum mechanics just doesn't tell you what they are. Hidden variables. Einstein thought the second option was more reasonable. Quantum mechanics was missing something, a deeper layer of reality where particles have definite properties whether you measure them or not. John Bell, an Irish physicist, proved in 1964 that Einstein was wrong. Bell derived an inequality, a mathematical relationship that any theory with local hidden variables must satisfy. Local means no faster than light influence. Hidden variables means the particles have definite properties before measurement. Bell showed that quantum mechanics predicts violations of the inequality. If entangled photons behave the way quantum mechanics says they should, they'll produce correlations that no local hidden variable theory can explain. Experiments tested it. The first decisive test came in 1982, performed by Alain Aspect and his team in France. They created entangled photon pairs and measured their polarizations at two separate detectors. The results violated Bell's inequality. Quantum mechanics was right. Einstein was wrong. The photons did not have definite polarizations before measurement. The measurement of one photon instantaneously affected the state of the other, not because a signal traveled between them, because they were entangled, one system, not two. That result has been confirmed hundreds of times since then, with better equipment, over longer distances, closing every possible loophole. Entangled photons have been separated by more than 1,000 kilometers and still show the correlations. Quantum mechanics works. Non-locality is real. The universe allows instantaneous connections between distant objects. It doesn't allow faster-than-light communication. You can't use entanglement to send information, but the connection is there, real, measurable, impossible to explain with any local theory. What does that mean for the photon? It means a photon can be in two places at once, and not in the trivial sense of a wave function spreading out. Two entangled photons, separated by a galaxy, are not two independent photons. They're two aspects of a single quantum state. Disturb one, and you disturb both. Not because of a force, not because of a signal, because they're connected at a level deeper than space and time. That connection doesn't fit into any classical picture of reality. Objects are supposed to be local. What happens here is supposed to be independent of what happens there, unless something travels between the two locations. Photons break that rule. They connect distant points in space without anything traveling between them. Entanglement is now a resource, something you can use to do tasks that are impossible classically. Quantum teleportation, developed in the 1990s, uses entangled photons to transmit the quantum state of a particle from one location to another without the particle itself making the trip. You destroy the original, send some classical information about the measurement result, and reconstruct the state at the destination using the entangled photon. It's not Star Trek. You're not teleporting matter. You're teleporting information. But it's information that can only be transmitted if you have entanglement. Classical communication isn't enough. Quantum computing relies on entanglement. A quantum computer with many qubits in an entangled state can explore an exponentially large space of possibilities simultaneously, solve certain problems faster than any classical computer ever could. Photons are one of the leading platforms for building quantum computers. They're easy to entangle, easy to manipulate, and they don't lose their quantum properties quickly. The challenge is scaling up. Entangling two photons is routine. Entangling 1 million photons in a controlled way is a nightmare. But the fact that it's possible at all, that you can create these vast, interconnected quantum states and use them to compute, is a direct consequence of the non-locality photons exhibit. The strangeness is a feature, and yet nobody knows why entanglement works. The math is clear, the experiments confirm it. But the mechanism, the reason the universe is built this way, is missing. Why do quantum states extend across space? Why does measurement here affect a system there? What is the quantum state made of? Is it a real physical thing, or is it just a mathematical tool for predicting measurement outcomes? Physicists argue about this. Some think the wave function is real, an actual entity that exists in the world. Others think it's just information, a representation of what you know about a system. The debate isn't settled, and until it is, the photon remains wrapped in mystery. The philosophical implications go deeper. Wave-particle duality, measurement collapse, entanglement, all of it forces you to question what you mean by real. Classical physics assumed objects have definite properties independent of observation. A photon has a position, a particle has a velocity. You measure it to find out what it is, but the property was there before you looked. Quantum mechanics says no, the photon doesn't have a position until you measure it. It has a range of possible positions, a probability distribution, and measurement picks one. But before measurement, the position isn't hidden, it isn't unknown, it doesn't exist. That's not ignorance, that's ontology. The nature of being. Classical physics says reality is made of things with properties. Quantum mechanics says reality is made of potentialities, possibilities. The photon is not in a definite state. It's in a superposition of states, multiple realities layered on top of each other. Measurement collapses the superposition, selects one reality, discards the others. Or, if you believe many worlds, measurement doesn't collapse anything. All the realities persist, branching into separate universes. Either way, the photon before measurement is not a thing. It's a cloud of potential things. And that's a fundamentally different kind of existence. Philosophers have been wrestling with this for a century. If properties don't exist until you measure them, does the universe exist when you're not looking? Does the moon disappear when nobody's watching it? Einstein asked that question mockingly as a reductio ad absurdum of quantum mechanics. The obvious answer is yes, the moon is still there. But quantum mechanics doesn't give you that answer easily. The moon is a macroscopic object made of countless particles, and the quantum effects average out so thoroughly that it behaves classically. But in principle, the moon is in a quantum superposition. It's here and slightly over there simultaneously. You never notice because the superposition is so close to a definite state that the difference is immeasurable. But it's there. This is why measurement is so important. It's the boundary between the quantum world and the classical world. Cross that boundary and potentialities become actualities. Superpositions become definite outcomes. The universe goes from might be to is, and we don't understand how. We don't understand where the boundary is or why it exists. Some think it's observer-dependent. Some think it's scale-dependent. Some think it's an illusion and there is no boundary at all, just branches splitting, or pilot waves guiding particles, or something else we haven't thought of yet. The photon, because it's so well understood mathematically and so thoroughly tested experimentally, throws all of this into sharp relief. Every photon experiment is also a test of the foundations of quantum mechanics. The double slit tests superposition. Bell tests test non-locality. Delayed choice experiments, where you decide whether to measure which slit the photon went through after it's already passed the slits. Test whether the past is fixed or malleable. Every time, quantum mechanics wins. The photon behaves exactly as the theory predicts. But the theory doesn't tell you what the photon is. It tells you what to expect when you measure it. there's a difference. And so the photon remains an enigma, the simplest quantum particle. No mass, no charge, no internal structure, just energy and momentum, frequency and wavelength, locked together by Planck's constant. We've measured it to absurd precision. We've built entire industries on manipulating it. We've used it to probe the universe from the cosmic microwave background to the spectra of distant galaxies. We've entangled it, teleported it, used it to encrypt information and to compute. We understand its behavior better than any other object in physics, but ask what it is, and the answer fractures into interpretations. Ask how it knows to behave like a wave or a particle, depending on how you measure it, and the silence is deafening. Ask why it exists outside of time, why it connects distant points in space, why observation changes its nature, and you hit the edge of what physics can currently explain. The photon is the key to understanding the electromagnetic force, the nature of light, the structure of atoms, the history of the cosmos. It's also the key to understanding the limits of human knowledge, the place where our equations work perfectly and our intuition fails completely. Richard Feynman said, "Nobody understands quantum mechanics." He was talking about photons, about the fact that you can learn the rules, master the calculations, predict every experiment, and still not grasp what's actually happening. The photon is the universe's way of reminding you that reality is under no obligation to make sense. It just has to be consistent. And it is. Photons follow rules, rigid, mathematical, testable rules. But the rules describe a reality so far removed from everyday experience that calling it strange is underselling it. That strangeness is not a bug. It's the point. The photon, by existing the way it does, by refusing to fit into classical categories, forces physics forward. Every attempt to explain it has led to deeper theories. Maxwell's equations unified electricity, magnetism, and light. Planck's quantization opened the door to quantum mechanics. Einstein's photons explained the photoelectric effect and hinted at wave-particle duality. Dirac's field theory laid the foundation for QED. Feynman's diagrams gave us a language for particle interactions. Bell's theorem proved non-locality. Every step, every breakthrough came from trying to understand what a photon is and how it works. And every answer raised new questions. The photon is not done teaching us. Quantum gravity waits. A theory of everything waits. The measurement problem waits. The nature of consciousness, the structure of space-time, the reason the universe is quantum instead of classical, all of it is tangled up in the same mysteries the photon embodies. Solve those and you'll finally understand light. Or maybe you'll just find deeper mysteries underneath. That's how science works. You peel back one layer and there's another. The photon is the oldest mystery in physics and the newest frontier. We've been studying it for centuries. We'll be studying it for centuries more. And every time you turn on a light, every time you see a reflection, every time a photon from the sun crosses 150 million kilometers and lands on your skin, the mystery is right there, invisible, undeniable, eternal. So here we are, 120 years after Einstein published a 20-page paper that most physicists initially ignored, trying to explain what light actually is. And the best answer physics can give you, after a century of experiments, after quantum field theory, after measuring the electron's magnetic moment to 12 decimal places, after building lasers and solar panels and quantum computers on the back of photon physics, is this. Light is an excitation of the electromagnetic field, a ripple, a disturbance, a quantum that carries energy and momentum from one place to another at exactly 299,792,458 meters per second, always, no exceptions, Because it has no mass to slow it down. Because the universe locked it at the cosmic speed limit and threw away the key. That's the answer. And it explains everything. How atoms emit light. How forces work. How the cosmos communicates across billions of light years. It predicts every photon interaction with terrifying precision. And yet, ask what the photon actually is when nobody's looking. Ask how it decides to behave like a wave or a particle depending on your measurement apparatus. Ask why it exists outside of time from its own perspective, and the framework cracks, not because the math is wrong. The math works. Because the question demands an answer in terms humans understand, and the photon doesn't care what humans understand. The photon is not a thing. It's a phenomenon, a messenger that connects charged particles across space, that makes vision possible, that built the structure of the universe one quantum interaction at a time. It's been ticking away since 380,000 years after the Big Bang, filling the cosmos with light, and it will keep going long after every star burns out. Traveling, always traveling, carrying information from there to here at a speed nothing else can match, and experiencing none of it, not 1 second, not 1 meter. For the photon, the journey you measure in billions of years is instantaneous. Emission and absorption are the same event. The universe has a beginning and an end, and from the photon's perspective, they're happening right now. You will never hold one. You will never slow it down to get a good look. The instant it stops being in motion, it stops being a photon. Its energy transferred, momentum delivered, gone. The most thoroughly studied object in the history of science is also the most elusive. We've built entire civilizations on manipulating it. We still don't know what it is, and maybe that's the point. Maybe the photon isn't hiding an answer. Maybe it's showing us that the universe at its foundation is stranger, deeper, and more beautiful than any explanation